At what point does space stop expanding? It's a question that feels like it should have an answer. We picture the universe as some kind of bubble, pushing its way into a black nothingness. We imagine an edge, a final frontier, where the expansion must just stop. And from there, the other questions just fall into place. How fast is it going? What is it expanding into? And when does it end? Welcome to the Science for Deep Sleep. If this kind of calm exploration into the universe helps you unwind, consider liking the video and subscribing to the channel. And wherever you are right now, whether near an ocean, a forest, a city, or somewhere quiet in between, feel free to share where you're watching or listening from. For nearly a century, we've known the universe is getting bigger. But chasing down an answer to, when will it stop, has led cosmologists to a staggering, almost unnerving conclusion. The real answer is far stranger, more profound, and more mind-bending than a simple, when. It reveals that the very question we're asking, the one that seems so logical, might be completely wrong. What if the universe isn't expanding into anything? What if there is no edge, no outside? And what if the idea of stopping is a cosmic misdirection, distracting us from the true, bizarre fate of everything? To find the answer, we can't look for a stopping point. Instead, we have to tear down our most basic intuitions about space, time, and reality itself. The echo of a beginning. Our story starts not with an end, but with a revolutionary discovery about our cosmic origins. For most of human history, the universe was seen as this static, eternal, and unchanging stage. That was the view from Aristotle to Newton. Even Einstein originally thought so. The stars were fixed, the heavens constant, a perfect and permanent machine. But in the early 20th century, that timeless portrait began to crack. The first clues came from an American astronomer named Vesto Slipher. In the 1910s, while looking at what were then called spiral nebulae, fuzzy patches of light we now know are entire galaxies, he noticed something odd. The light from most of them was stretched out, shifted towards the red end of the spectrum. This is called redshift, and it's a cosmic scale version of the Doppler effect. It's why an ambulance siren sounds higher as it races towards you and lower as it speeds away. The sound waves get compressed as the source approaches and stretched as it recedes. Light does the same thing. When something in space moves away from us, its light waves get stretched, making it appear redder. Slipher had found that nearly all the galaxies he could see were redshifted, they were all moving away from us. But his quiet observations were just the prelude. The cosmological bombshell was dropped in 1929 by Edwin Hubble. Using the powerful Hooker telescope at Mount Wilson Observatory, Hubble measured the distances to these galaxies with incredible accuracy. When he plotted their distances against how fast they were moving away, he found a stunningly simple relationship. The farther away a galaxy was, the faster it was receding from us. This wasn't some random chaos. It was a systematic, orderly, and universal expansion. Every galaxy seemed to be rushing away from every other galaxy. This discovery, Hubble's law, completely overturned our picture of the universe. It was the first hard evidence that the cosmos wasn't static but dynamic. And it implied something even more mind-bending. If everything is moving apart now, then in the past, everything must have been closer together. Rewinding this cosmic movie leads to a moment of unimaginable density and heat. A single point containing the entire observable universe. This, of course, was the seed of the Big Bang Theory. The universe wasn't eternal. It had a beginning, about 13.8 billion years ago, and has been expanding ever since. For decades, the big question in cosmology was, what's the final fate of this expansion? Gravity, the universe's cosmic brake, pulls everything together. It seemed obvious that this relentless pull would gradually slow the expansion down. The universe's destiny was a balancing act. If there was enough matter, and thus enough gravity, the expansion would eventually halt, reverse, and collapse in on itself in a fiery, big crunch. If there wasn't enough matter, the expansion would slow but never quite stop, coasting forever into a cold, dark future. For most of the 20th century, astronomers were locked in a great debate, trying to weigh the universe to figure out which path we were on. But in 1998, the universe threw us the biggest curveball in the history of science. Two teams of astronomers were using Type Ia supernovae, exploding stars with a very consistent brightness, to measure the expansion rate over vast distances. Think of them as cosmic standard candles, because you know how bright they truly are. How faint they appear tells you how far away they are. This lets you precisely measure how the expansion rate has changed over time. Everyone expected to find the expansion was slowing down. They found the exact opposite. The distant supernovae were even fainter than they should have been, meaning they were farther away than a decelerating universe would allow. The only explanation was that the expansion of the universe wasn't slowing down at all. It was speeding up. Something was actively pushing the universe apart, overpowering gravity. The scientists behind this discovery were awarded the 2011 Nobel Prize in Physics, and their finding gave birth to the greatest mystery in modern cosmology, a mysterious, anti-gravitational force we call dark energy. This discovery of cosmic acceleration completely changed the game. It made the old question, when does space stop expanding, even more urgent, but also infinitely more complex. If some mysterious energy is pushing everything apart faster and faster, does that mean it will never stop? To answer that, we first have to realize that the pictures we use to imagine this expansion are leading us astray. The analogy that breaks the mind. When we try to grasp an expanding universe, our minds instinctively grab onto a simple model, the balloon. Imagine drawing dots on a balloon. As you inflate it, every dot moves away from every other dot. An ant on any one of those dots would see all the other dots receding, and the farther away a dot is, the faster it appears to move. This seems to perfectly capture what Hubble saw. Crucially, the dots themselves aren't moving across the balloon's surface. The rubber of the balloon, the space between them, is itself stretching. This analogy is brilliant because it solves a huge misconception. It shows that the expansion isn't like an explosion where galaxies are shrapnel flying through space from a single point. No, space itself is what's expanding. The galaxies are just carried along for the ride, like raisins in a rising loaf of bread. This also elegantly explains why there's no center of the universe. On the balloon's surface, no dot is special. From any dot, it looks like you're at the center. So, our Milky Way isn't the center of the universe. Every observer in every galaxy sees the same thing, everything else rushing away from them. But here's where the analogy becomes a trap. It works for a 2D surface, but it breaks down when we apply it to our 3D universe. Why? Because we automatically picture the balloon expanding inside a room. We see the balloon getting bigger, pushing the air in the room aside. This leads us right back to that flawed question. What is the universe expanding into? The balloon tricks us into thinking there has to be an outside. But the universe, by definition, is everything. All of space, all of time, all matter and energy. If the universe contains all of space, there can be no space outside of it for it to expand into. This is the first mental leap we have to make. The expansion of the universe is not the expansion of matter into space, it is the expansion of space itself. Everywhere, at once. Think back to the raisin bread, but imagine it's an infinite loaf. As the dough rises, the infinite loaf just becomes, well, more infinite. The distance between any two raisins increases, but there is no edge, no center, and no outside. This is a leading possibility for the shape of our universe, that it's spatially infinite. If so, it was always infinite, even at the Big Bang. The Big Bang wasn't an explosion in space, it was an explosion of space that happened everywhere at once. This is an incredibly tough concept to wrap your head around. Our brains are wired for a world of edges and containers. But there's another, equally mind-bending possibility. The universe could be finite, but still have no edge. How? Back to the balloon. The 2D surface of the balloon is finite. You can measure its area, but it has no edge. An ant can walk on it forever and never fall off. It will just circle the globe and end up back where it started. Cosmologists think our 3D universe could be like that, but in a higher dimension. The 3D surface of a 4D hypersphere. We could travel in what feels like a straight line, only to eventually end up right back where we started, having circumnavigated the entire cosmos. In this model, the universe has a finite volume, but still no edge, no center, and no outside. Whether the universe is infinite or finite and unbounded, the conclusion is the same. The expansion of space doesn't need an outer void to expand into. It is an intrinsic stretching of reality itself. So, the question isn't about finding a stopping point in space. The real question is about finding a stopping point in time. Will the process of expansion itself ever stop? For that, we have to turn to the force that drives it, dark energy. The deeper truth of spacetime. To really get why the universe expands into itself, we have to go deeper than analogies. We have to talk about Einstein's general theory of relativity. Before Einstein, space was just the boring, fixed stage where everything happened. Einstein's genius was realizing that space and time are fused together into a single fabric, spacetime. And this fabric isn't a passive stage, it's an active player. He showed that matter and energy tell spacetime how to curve. And in turn, the curvature of spacetime tells matter and energy how to move. This is what we feel as gravity. Think of a bowling ball on a rubber sheet. It creates a dip. A marble rolled nearby will follow that curve, spiraling in. It's not being pulled by a mysterious force. It's just following the straightest possible path through a curved environment. The sun doesn't hold the Earth in orbit with an invisible rope. It creates a huge dent in spacetime that the Earth is constantly falling around. This completely changes our understanding of cosmic expansion. When we say, space is expanding, we mean that the very geometry of spacetime, the fundamental grid lines on the cosmic map, is stretching everywhere. The galaxies aren't really moving through space. The space between them is literally growing. And this leads to a wild fact. Because it's spacetime itself that's expanding, the expansion isn't limited by the speed of light. Einstein's theory says nothing can travel through space faster than light. But it places no speed limit on the expansion asterisk of space itself. If you look at a galaxy far enough away, the space between you and it is stretching so much that its total recession speed is faster than the speed of light. That's not breaking physics. The galaxy isn't rocketing through space. It's just sitting there while the fabric of spacetime between us stretches so fast it appears to us to be receding faster than light. In fact, most galaxies in the observable universe are already moving away from us faster than light. We can see them because the light they emitted long ago, when they were closer, is just now reaching us. But the light they are emitting today will never make it. They've crossed a cosmic point of no return, the cosmic event horizon. As the expansion accelerates, more and more galaxies will cross this horizon, their light fading until they blink out of our sight forever. This brings us back to what this space is. In modern physics, it's understood as a field. And quantum field theory tells us that even empty space, a perfect vacuum, seeds with a baseline energy, known as vacuum energy. Virtual particles constantly pop in and out of existence. This energy has a real gravitational effect. And right now, this energy of nothing is our best candidate for dark energy. It acts like an anti-gravity, a repulsive pressure baked into the fabric of space itself. So, as space expands, more space is created. And because this vacuum energy is a property of space itself, more of this energy is created. This new energy then causes space to expand even faster, which in turn creates more space and more energy. It's a runaway feedback loop. The universe isn't just expanding, its expansion is being fueled by the very creation of more space. So there's no stopping point in space because there's no edge. The only question left is whether the process will stop in time. The answer depends entirely on the true nature of dark energy. Is it constant? Is it weakening? Or is it getting stronger? The answer to that will write the final chapter of the cosmos. The cosmic tug-of-war and a shocking twist. The discovery of dark energy kicked off a cosmic tug-of-war. On one side, you have gravity, the pull of all matter and dark matter, trying to rein in the expansion. On the other side is dark energy, this mysterious repulsive force, pushing everything apart. Dark energy makes up about 70% of the universe, dark matter about 25%, and everything we can see, stars, planets, you and me, is just the remaining 5%. Right now, dark energy is winning, and its lead is growing. As the universe expands, matter gets spread out, and its gravitational pull gets weaker. But dark energy seems different. Our best model, called the lambda-CDM model, assumes dark energy is a cosmological constant. This means its density is constant. A cubic meter of space today has the same amount of dark energy as a cubic meter of space a billion years ago. It doesn't dilute. This creates a runaway process. More space means more dark energy, which means faster expansion, which means more space. However, the idea that dark energy is perfectly constant is just the simplest assumption, and it's now facing serious challenges. This is where things get really interesting, because the whole story we've been telling for 25 years might be wrong. One major puzzle is the Hubble tension. Measurements of the expansion rate using nearby objects, like supernovae, give a higher value than measurements based on the light from the very early universe. For instance, research in 2025 by Dan Skolnick found a local expansion rate of 76.5 kilometers per second per megaparsec. But data from the early universe, measured by telescopes like the Atacama Cosmology Telescope, points to a slower rate of 67 to 68 kilometers per second, MPC. For years, this stubborn discrepancy suggested our standard model of cosmology might be incomplete. However, other recent work may be easing the tension. A 2025 analysis by Wendy Friedman combining data from the Planck satellite and the James Webb Space Telescope found a value of 70.4 kilometers per second, MPC, splitting the difference and suggesting the standard model might hold up after all. The debate is fierce, but a stunning twist came in late 2025. A peer-reviewed study from a team at Yonsei University made a groundbreaking claim. They argue that the brightness of Type Ia supernovae, the very standard candles used to discover dark energy, is biased by the age of their parent stars. Supernovae from younger star systems appear to be systematically dimmer. After correcting for this age bias, they reanalyzed the data and came to a revolutionary conclusion. The evidence for cosmic acceleration vanishes. Their research, published in * monthly notices of the Royal Astronomical Society, suggests that the universe may have already entered a phase of decelerated expansion. If this is confirmed, it would be a paradigm shift in cosmology. It would mean that dark energy is not a constant, but is evolving and weakening over time, far more rapidly than we thought. The entire foundation for the accelerating universe, a Nobel Prize-winning discovery, is suddenly being called into question. The fate of the universe is not a settled question. It is an active and explosive field of research, where the final chapter could go one of three very different ways. The end of everything, freeze, rip, or crunch. Armed with this new, unfolding drama, we can finally ask the right question. Will the process of expansion ever stop in time? The answer hinges on the true nature of dark energy, and there are three main scenarios for how this all ends. Scenario 1. The Big Freeze, or heat death. This was the leading theory for years, based on the idea that dark energy is a constant force, W equals -1. In this future, the accelerating expansion never stops, it just goes on forever. Over the next 100 billion years, every galaxy not gravitationally bound to us gets pushed beyond our cosmic horizon. The night sky goes dark. Our local group of galaxies will eventually merge into one supergalaxy, a lonely island in an endless, empty void. The stars inside this mega-galaxy will burn for trillions of years, but eventually, the fuel runs out. The stars die, one by one, leaving behind a graveyard of black holes, neutron stars, and cold, dead white dwarfs. Even the black holes aren't forever. Through Hawking radiation, they will slowly evaporate over truly unimaginable timescales, up to 10 to the power of 100 years. What's left is the Big Freeze. A universe that's almost a perfect vacuum, empty, dark, and near absolute zero. All activity will have stopped. It's a quiet, bleak, and infinitely long end. Scenario 2. The Big Rip. This is the most terrifying end. It happens if dark energy is a phantom energy that gets stronger over time, where its equation of state parameter, W, is less than -1. This would lead to a runaway acceleration that tears the fabric of reality apart. The end would come with shocking speed. In the final billions of years, the repulsive force of dark energy would start to overpower everything. First, it would unbind galaxy clusters. Then, with millions of years left, it would tear apart galaxies themselves, flinging stars into the void. In the final moments, the process goes catastrophic. Planets would be ripped from their stars. Then, stars and planets themselves would explode as the repulsive force overwhelms the gravity holding them together. In the last fraction of a second, atoms themselves would be shattered. The universe ends not in a cold whisper, but in a devastating rip, as the expansion rate becomes infinite. Scenario 3. The Big Crunch. This is the oldest idea, and thanks to recent research, it's making a major comeback. For a big crunch to happen, gravity has to eventually win the tug of war. This is possible if dark energy is weakening over time, which is exactly what the bombshell 2025 Yonsei University study suggests. Their analysis, which corrected for supernova age bias, found that the universe might already be decelerating. If this is true, our cosmic acceleration is just a temporary phase. In this scenario, the expansion would continue to slow, eventually stop, and then reverse. The universe would begin to contract. Instead of redshift, we'd see blue shift as galaxies race toward each other. The cosmos would get hotter and denser. The final moments would be a mirror image of the Big Bang, with everything collapsing back into an infinitely hot, dense singularity. Some theories speculate this could lead to a Big Bounce, where the collapse triggers a new Big Bang, creating a new universe in an endless cycle. It's a poetic idea, but one that's still purely speculative. So, at what point does space stop expanding? We've seen that the question itself is flawed. There's no edge to stop *at. There's only a process, happening everywhere, whose ultimate fate is one of the biggest and most active debates in all of science. Will the universe expand forever into a cold, dark Big Freeze? Will phantom energy tear every atom apart in a violent Big Rip? Or, as shocking new evidence suggests, is dark energy already weakening, sending our cosmos hurtling back towards a fiery Big Crunch? Just a short time ago, the Big Freeze seemed like our destiny. Now, the consensus is shattered. The very evidence for acceleration is being challenged, breathing new life into the idea of a cyclical universe. We live in a remarkable time, where we might be witnessing a complete upheaval in our understanding of the cosmos. The answer to how it all ends is genuinely up for grabs. Our simple question forced us to confront the bizarre nature of reality. That space is a dynamic fabric, that nothing is full of energy, and that our ultimate destiny is written in a force we are only just beginning to understand. We may never find a stopping point in space, but the search has uncovered a story far stranger and more profound than we ever could have imagined. Space isn't expanding the way you think. We have all heard the phrase, "The universe is expanding." It is one of the first, most fundamental ideas we learn about the cosmos. In our minds, a picture forms, a sea of galaxies, all flying away from each other like shrapnel from some ancient explosion. We see them moving through the dark emptiness of space. It is a simple and powerful image. But it is also an image that is almost entirely incomplete. What if the galaxies are not moving through space at all? What if the idea of a central point of origin is a misunderstanding? The reality of our expanding universe is stranger than we imagine, and it hints at a profound and deeply weird truth hiding behind that simple phrase. Understanding this one idea can change how we see everything. It challenges our intuitions about distance, motion, and the fabric of reality itself. To understand how space expands, we must first unlearn what we think we know about space. Everything in the universe appears to be moving away from everything else. But here is the quiet paradox at the heart of modern cosmology. On the largest scales, nothing is truly moving. Not in the way we think. This is not a riddle, but a description of how reality works. It leads to some bizarre conclusions. It means there are galaxies receding from us faster than the speed of light, and yet, we can still see them. It means the universe has no center and is not expanding into anything. These are not just unusual facts, they are signposts, pointing to a different understanding of space and time. This is the story of how we discovered that the stage of the cosmos is not a fixed arena, but a dynamic, stretching entity, carrying us all along with it. The great misconception: shrapnel in the void. Let's begin with the picture most of us have in our heads. We can call it the shrapnel model of the universe. In this view, the Big Bang was an explosion at a specific point in a pre-existing empty void. From this center, all matter erupted outwards. Galaxies, being clumps of that matter, were thrown into the emptiness and have been flying apart ever since. In this model, space is like a vast, dark room. The galaxies are like marbles shot out from its center. When we see that farther galaxies are moving away faster, it seems to suggest they simply had a greater push from the initial event. Our own Milky Way is just one piece of this shrapnel. By measuring the speed and direction of all the other pieces, we could theoretically trace everything back to the single point where the explosion happened. This model feels intuitive. It is based on every experience we have with explosions. There is a center, an outward rush, and a surrounding space it all expands into. For many years, even some scientists held a similar view. But this picture, as tidy as it is, leads to questions that do not have logical answers. For instance, if the universe is expanding from a central point, where is that point? We look out in every direction and see galaxies receding from us, which gives the illusion that we are at the very center. An observer in a galaxy a billion light-years away, however, would see the exact same thing. How can every location be the center? And what of an edge? If the universe is a finite sphere of shrapnel expanding into a void, there must be an outermost layer of galaxies. What would one see from there? A wall of pure blackness, the empty stage into which the cosmos is expanding. This idea does not align with our observations. The universe appears broadly the same in every direction, a concept cosmologists call the cosmological principle. The greatest problem, however, involves one of physics' most fundamental laws. We observe galaxies so far away that they are receding from us faster than the speed of light. Albert Einstein's theory of special relativity states that nothing with mass can travel through space faster than light. So how is this possible? Is Einstein's theory wrong? Or is our picture of expansion the thing that is broken? The shrapnel model crumbles under these paradoxes. The solution required a leap away from objects moving through space, and toward the idea that space itself is what moves. The fabric of spacetime, a new reality. The revolution in our understanding began with Albert Einstein. His general theory of relativity in 1915 rewrote our concept of gravity. Where Newton saw an invisible force, Einstein revealed gravity as a consequence of the shape of the universe. He proposed that space and time are woven together into a four-dimensional fabric, spacetime. Massive objects warp this fabric, and what we feel as gravity is simply the curvature of spacetime. But Einstein's equations held a surprise, a prediction so strange that he initially refused to accept it. They showed that this fabric of spacetime could not be static, it had to be either expanding or contracting. Believing in a static, eternal universe, Einstein added a cosmological constant to his equations to force them to stand still. He would later call this his greatest blunder. Proof that his original equations were right came just over a decade later. In the 1920s, astronomers like Vesto Slipher observed what were then called spiral nebulae. He noticed the light from these objects was almost always shifted toward the red end of the spectrum. This redshift is a cosmic version of the Doppler effect, like a siren's pitch changing as it moves away. It meant these nebulae were moving away from us at incredible speeds. It was the astronomer Edwin Hubble who put the pieces together. Using the telescope at Mount Wilson Observatory, he measured the distances to these nebulae, proving they were not clouds in our own galaxy, but entire, island universes, millions of light years away. In 1929, he combined his distance measurements with Slipher's redshift data and found a simple relationship. The farther away a galaxy was, the faster it was moving away from us. This was the first concrete evidence that the universe was expanding, just as Einstein's raw equations had predicted. But it wasn't an expansion of matter in space. It was an expansion of space itself. This concept is called the metric expansion of space. The most famous analogy is raisin bread. Imagine a lump of dough with raisins scattered throughout. The dough is space-time, and the raisins are galaxies. As the bread bakes, the dough expands, and every raisin moves away from every other raisin. The raisins are not moving through the dough. They are being carried apart as the dough itself expands, creating more space between them. From the perspective of any single raisin, all other raisins appear to be rushing away. A nearby raisin moves away slowly, as there is little dough expanding between them. A distant raisin moves away much faster, because there is a great deal of dough expanding between them. This perfectly explains Hubble's law. It also solves the paradoxes of the shrapnel model. There is no center. In the expanding dough, every raisin sees itself as the center. The expansion happens everywhere. There is no edge. The dough is not expanding into anything. The expansion is a property of the dough itself. And the galaxies moving faster than light? This is where the distinction is crucial. Einstein's speed limit applies to objects moving through space. But metric expansion is the space itself stretching. There is no known limit to how fast spacetime can expand. For 2 points very far apart, the cumulative effect of all the stretching dough between them can add up to a recession speed faster than light. The galaxy is not breaking a cosmic law. It is not the raisin moving, but the bread rising. This single, strange idea unlocked modern cosmology. What actually expands? This idea, that space itself is stretching, leads to a natural question. If the space between galaxies is expanding, is the solar system expanding? Is the Earth? Am I? The good news is, Brooklyn is not expanding. The reason comes down to a quiet, cosmic tug of war. The metric expansion of space is a real phenomenon, a gentle, persistent push happening everywhere. But on local scales, this push is incredibly weak. At the current rate, space expands by about 7% every billion years. Over the vast, mostly empty distances between galaxy clusters, this tiny effect adds up and dominates. But on smaller scales, other forces are much stronger. Within our solar system, gravity completely overpowers this gentle push. The Earth is not getting farther from the Sun because the Sun's gravitational pull creates a stable, bound system. The expansion is still happening between the Earth and the Sun, but it's like trying to move a freight train by blowing on it. Gravity holds the solar system together, and it is far too powerful for the expansion to overcome. The same is true on even smaller scales. Within the Milky Way, the collective gravity of billions of stars holds the structure together. In fact, our nearest large galactic neighbor, Andromeda, is moving towards us. We are part of the local group, a cluster of galaxies gravitationally bound to each other. Within this group, gravity is in charge. And for you, or the atoms that make you up, the electromagnetic and nuclear forces are orders of magnitude stronger than both gravity and cosmic expansion. The bonds holding your molecules together are not stretching. The ruler on your desk is not getting longer. So, what actually expands are the vast, empty voids between gravitationally unbound structures like galaxy clusters. Think of space as a fabric and gravity as a staple. Where matter is dense, gravity staples the fabric of spacetime together, preventing it from stretching. Your body and the solar system are heavily stapled regions. But in the enormous gaps between these areas, the fabric is free to stretch. This is the cosmic dance between the relentless push of expansion and the local grip of gravity. On all the scales that matter to our lives, gravity wins. A crisis in the cosmos, the Hubble tension. For decades, this picture of an expanding universe formed the bedrock of cosmology. Scientists worked to refine one number that governs it all, the Hubble constant, which tells us how fast the universe is expanding. But as our instruments became more precise, a crack appeared in our understanding. A disagreement has emerged between the two best ways of measuring this constant. The problem is known as the Hubble tension. The first method looks at the late universe, the cosmos relatively nearby. Astronomers use standard candles, like Cepheid variable stars and Type Ia supernovae, whose true brightness is known. By comparing their known brightness to how bright they appear from Earth, we can calculate their distance. Combining these distances with redshift measurements from telescopes like Hubble and James Webb gives a Hubble constant of around 73 to 74 km per second per megaparsec. The second method is completely different. It looks at the early universe, studying the faint glow from the Big Bang, called the cosmic microwave background, CMB. This is a baby picture of the universe at only 380,000 years old, containing tiny temperature fluctuations. Using our best model of physics, scientists can take this baby picture and predict how fast the universe should be expanding today. This method, using data from missions like the Planck satellite, gives a different answer. A Hubble constant of around 67 to 68. That difference may not sound like much, but with the precision of these measurements, it is a 5 sigma discrepancy, the gold standard for a new discovery in physics. The chance it is a random error is less than 1 in 3.5 million. Our two best methods give two different answers. It shows that science works and that data can change our ideas, even if those ideas are deeply entrenched. Recently, these tensions have grown. The latest 2026 analysis from the Dark Energy Survey, which for the first time combined all 4 of its cosmological probes, provided constraints on the universe's composition that are more than twice as strong as its previous analyses. This new data revealed that the long-standing discrepancy in how matter clusters in the universe has become more pronounced. This isn't just a numerical problem, it's a clue. It is a loose thread in the tapestry of cosmology. Pulling on it might unravel our picture of the cosmos, leading to a new revolution in physics. The universe is telling us we have missed something. The runaway universe and the mystery of dark energy. Just as the Hubble tension began to emerge, cosmology was still absorbing an even bigger shock: the discovery that the universe's expansion is speeding up. For most of the 20th century, scientists believed the expansion must be slowing down, held back by the inward pull of gravity from all the matter in the cosmos. In 1998, two teams set out to measure this deceleration using Type Ia supernovae. They expected to find that distant supernovae were slightly brighter than predicted, meaning the expansion had slowed over time. They found the opposite. The distant supernovae were dimmer, and therefore farther away than they should have been. This could only mean one thing: for the past several billion years, the expansion has been accelerating. This discovery earned its leaders the 2011 Nobel Prize in Physics. It was as if you threw keys in the air and, instead of falling, they shot upwards faster and faster. Something was pushing them. Scientists gave this mysterious, repulsive force a name: dark energy. We cannot see it or measure it directly, only its effect. And its effect is profound. According to our standard model of the universe, a model that is itself being questioned by the Hubble tension, this energy makes up about 70% of the mass-energy content of the cosmos. Normal matter, the stuff of stars and is a mere 5%. We live in a universe dominated by substances we do not understand. What is dark energy? The leading idea is that it is the cosmological constant Einstein proposed, an intrinsic energy of space itself. As space expands, more of this vacuum energy appears, creating a repulsive force that pushes everything apart even faster. Another idea is quintessence, a dynamic field that could change over time. An evolving dark energy like this could potentially help explain the Hubble tension. Whatever its nature, the discovery of dark energy rewrote our cosmic destiny. The ultimate fate, the discovery of accelerating expansion, has forced us to reconsider the end of everything. With dark energy pushing the accelerator, the old idea of a big crunch, a universe collapsing back on itself, seemed unlikely. Instead, we appeared to be heading towards a much colder, lonelier finale. Based on dark energy being a constant, the most probable fate is the Big Freeze. The accelerating expansion would continue forever. In a couple of trillion years, all galaxies outside our local, gravitationally bound group will have receded beyond our cosmic horizon. The sky, from our merged Milkomeda galaxy, will become empty. Future astronomers would see only an island universe, with no evidence that a vaster cosmos ever existed. After trillions of years, the last stars would burn out, leaving a dark, cold, and expanding graveyard of stellar remnants. Eventually, even these would decay, leaving a silent, empty eternity approaching absolute zero. And yet, very recently, the picture has begun to change again. The Big Freeze is based on dark energy being a constant, but what if it evolves? Some have theorized about a Big Rip, where a strengthening, phantom energy would tear apart galaxies, stars, and even atoms. But new analysis from Cornell researchers, published in February 2026, has suggested another possibility. Their work indicates that dark energy might be weakening and could even become negative in the distant future. This could cause the expansion to halt, reverse, and send the universe collapsing back towards a big crunch billions of years from now. This is still an area of active research, but it underscores how little we truly know. We find ourselves in a strange position. We have unraveled the misconception of our universe's expansion only to find deeper mysteries. We have learned that space itself is an active participant in the cosmic story, stretching and growing. But in doing so, we have uncovered a crisis in our measurements and a mysterious, dominant energy we cannot explain. We have peered toward the end of everything, only to find that the story is not yet written. The universe isn't expanding the way you think. It seems the more we learn, the more the cosmos stretches the very idea of what reality can be. What happens the moment space stops expanding? For as long as we have had an understanding of the sky, we have observed a fundamental truth about our universe. On the largest scales, everything is moving away from everything else. For 13.8 billion years, the fabric of space has been expanding. Every distant galaxy has been carried along on this cosmic tide, a faint echo of the universe's origin in the Big Bang. This expansion has shaped our understanding of the cosmic past, the present, and what we thought was its future. But let us consider a different possibility. A single moment when the expansion that has defined the universe's history comes to a halt. The constant outward movement ceases. The universe, for the first time, holds still. What would happen in the moments and eons that follow? Would the cosmos exist in a delicate, static balance, or would this mark the beginning of a great reversal? The answer is complex. It is a story of a competition between fundamental forces that has been ongoing since the first second of time. To understand what happens when space stops expanding, we must first look at why it was expanding, and how our understanding of that expansion has evolved. The expanding reality. The story of our expanding universe began in the 1920s with the astronomer Edwin Hubble. Using the powerful telescopes of his time, he made an observation that would change our perception of the cosmos. He found that the light from distant galaxies was not the color it was expected to be. It was stretched, shifted toward the red end of the spectrum. This phenomenon, known as redshift, acts as a cosmic Doppler effect. Much like the pitch of a siren lowers as it moves away, the wavelength of light from a receding galaxy is stretched. Hubble's observations revealed not only that nearly all galaxies were moving away from us, but that their recession speed was proportional to their distance. This was not a picture of galaxies traveling through space. This was evidence of space itself expanding, carrying the galaxies with it. A common analogy is to imagine dots on the surface of a balloon. As the balloon is inflated, every dot moves away from every other dot, yet no single dot is the center. Our universe, Hubble's work showed, was like that balloon, and it was growing. This discovery provided the first strong evidence for the Big Bang theory, the idea that the universe began in an incredibly hot, dense state and has been expanding and cooling since. For much of the 20th century, the expansion was seen as the leftover momentum from this origin. The primary question for cosmologists then became, will it expand forever? The fate of the universe was understood as a tug-of-war on a cosmic scale. On one side was the outward momentum of the expansion. On the other was the inward pull of gravity. Every particle of matter in the universe exerts a gravitational pull on every other particle, acting as a constant brake on the expansion. The question, then, was a matter of cosmic inventory. Is there enough matter, and therefore enough gravity, in the universe to eventually halt the expansion and reverse it? This was quantified by a value called omega. If omega were greater than 1, gravity would win, and the universe would collapse. If it were less than 1, the expansion would continue forever, though at an ever-slowing rate. For decades, astronomers worked to measure the mass of the cosmos to determine this value. The prevailing wisdom, based on their observations, was that gravity was slowing the expansion, but was not strong enough to stop it entirely. Then, in 1998, new evidence emerged that challenged this entire picture. The unexpected acceleration and the era of dark energy. Science is a process where established ideas are tested by new evidence. In 1998, the long-held assumption that the universe's expansion must be slowing down was confronted with surprising data. Two independent teams of astronomers were using a specific type of stellar explosion, a type Ia supernova, as a standard candle, to measure the history of cosmic expansion. A type Ia supernova occurs when a white dwarf star explodes with a predictable and uniform peak brightness. This allows astronomers to see one in a distant galaxy, measure its apparent brightness, and calculate its distance with precision. They are like cosmic lighthouses of a known wattage. The goal was to use these supernovae to map how the expansion rate had changed over time, expecting to measure the rate of its deceleration. The results, however, were not what anyone predicted. The most distant supernovae were fainter than they should have been in a slowing universe. This pointed to a remarkable conclusion. Those galaxies were farther away than the existing models predicted. For them to have traveled that far, the expansion of the universe had not been slowing down. In fact, for the last several billion years, it has been speeding up. This discovery, which was awarded the Nobel Prize in Physics in 2011, introduced one of the greatest mysteries in modern science: dark energy. The nature of this force that appears to overwhelm gravity on cosmic scales is still unknown. The leading hypothesis is that it is an intrinsic energy of the vacuum of space itself, sometimes called the cosmological constant. Unlike matter, which dilutes as space expands, this vacuum energy remains constant. As space expands, more space is created, and with it, more of this energy, which in turn pushes space to expand even faster. This dark energy is now thought to make up around 68% of the universe's total energy density. The normal matter that comprises stars, planets, and us is a mere 5%. Dark energy, this apparent anti-gravity force, became the deciding factor in the universe's ultimate fate. This discovery led to new, widely accepted scenarios for the end of the universe, both born from the idea of perpetual, accelerating expansion. Scenario 1: the Big Freeze. If dark energy is a constant, unchanging property of spacetime, then our universe is likely headed for an end that is not sudden, but slow, cold, and quiet. This scenario is known as the Big Freeze, or the heat death of the universe. The process has already begun. The accelerating expansion is pushing galaxies not gravitationally bound to us away at increasing speeds. Eventually, they will recede from us faster than the speed of light. This does not violate relativity, as nothing is moving through space that fast. Rather, the space between us and them expands so rapidly that light can no longer cross the gulf. Over billions of years, the night sky will gradually empty. From a future vantage point, every galaxy beyond our local group will fade from view, its light redshifted into oblivion. The cosmos we see today will be replaced by an immense darkness. Our own local group of galaxies will remain as an island, held together by gravity, in a vast and empty void. Within this island, the long, slow process of decay will continue. Over trillions of years, the gas and dust required for star formation will be exhausted. The era of stars will come to an end. The stars that remain will burn out. Sun-like stars will become white dwarfs. More massive stars will have already become neutron stars and black holes. Eventually, even the longest living red dwarfs will fade. The universe will become a silent graveyard of these stellar remnants. White dwarfs and neutron stars will cool until they are no warmer than the space around them. However, even this is not the end. On immense timescales, it's theorized that protons themselves may be unstable and could decay, causing matter to disintegrate into a sea of low-energy particles. The dead stars and frozen planets would simply evaporate. The only objects remaining would be black holes. Yet even they are not eternal. Through a process known as Hawking radiation, black holes slowly lose energy over almost unimaginable lengths of time. A supermassive black hole might take 10 to the power of 100 years to evaporate completely. After that, there would be almost nothing. The universe would have reached a state of maximum entropy. A vast, dark expanse filled with a sparse, near-zero energy soup of particles, so far apart they will never interact. Temperature will approach absolute zero. All meaningful processes will cease, forever. This is the heat death, the final state of a universe dominated by a constant dark energy. A more violent alternative, the Big Rip. The Big Freeze was long considered the most plausible end. But what if dark energy is not constant? What if its strength increases over time? This possibility leads to a very different scenario, the Big Rip. This hypothesis is based on a theoretical form of dark energy called phantom energy. Unlike a cosmological constant, the density of phantom energy would increase as the universe expands. This would create an accelerating acceleration, leading to a runaway expansion that becomes infinitely fast in a finite amount of time. If our universe is shaped by phantom energy, its end would not be a slow fade, but a rapid, systematic deconstruction of the cosmos. The process would begin with the largest structures. Hundreds of millions of years before the rip, the expansion would become strong enough to overcome the gravity holding galaxy clusters together, and they would dissolve. As the moment of the rip approaches, the force would overwhelm gravity on smaller and smaller scales. Millions of years before the end, galaxies themselves would be unbound. Stars would be flung into the expanding void. Months before the final moment, the forces holding solar systems together would fail. Planets would be torn from their stars. In the final minutes, the electromagnetic and gravitational forces holding solid objects together would be overcome. Planets and stars would come apart. Seconds before the end, the forces holding molecules and atoms together would fail. Then, in the last fraction of a second, the phantom energy would become infinitely strong. It would overcome the strong nuclear force, tearing apart atomic nuclei themselves. The fabric of spacetime would be torn asunder. The universe would cease to exist in the most complete way imaginable. For years, the discussion centered on these two possibilities: the cold, quiet Big Freeze or the violent, sudden Big Rip. But what if the science of the last quarter century was just one chapter in a longer story? New evidence, the story evolves. Science is a process of constant refinement. We thought the universe was static until evidence showed it was expanding. We thought the expansion was slowing until evidence suggested it was speeding up. For a quarter of a century, we have explored the consequences of that acceleration. However, more recent evidence hints at another potential shift in our understanding. In 2024, early data from the Dark Energy Spectroscopic Instrument, or DESI, showed subtle indications that dark energy might not be constant, but could be evolving over cosmic time. This was followed by new research published in late 2025 and early 2026. A team at Yonsei University re-examined the Type Ia supernovae observations. They proposed that there might be a bias in the data. Supernovae in younger galaxies, they found, could be systematically fainter than those in older galaxies. They suggested this might account for some of the dimness that was originally interpreted as acceleration. When they applied a correction for this proposed age bias, their analysis suggested a different cosmic history, one with no acceleration in the present era. In fact, it indicated the expansion may already be decelerating. Gravity might be slowly regaining the upper hand. This is a significant claim, and it's important to note that these findings are new and still being actively debated within the scientific community. It is not a closed case. However, this work has brought a long-discarded theory back into discussion. If dark energy is indeed weakening, then gravity is no longer fighting a losing battle, and the universe may not be destined to expand forever. The Big Crunch is once again a possibility. Following this, some physicists used the latest data to model this potential future. These models suggest the expansion could continue for roughly another 11 billion years before reaching its maximum size. After that, it might begin a slow contraction, ending in a Big Crunch approximately 20 billion years from now. If this is true, the accelerating expansion would have been a temporary phase in the universe's life. A phase that may now be ending. The return of the Big Crunch. With this new perspective, let us return to our original question. What happens the moment space stops expanding? In this scenario, that moment is not a beginning of stillness, but a turning point. It is the apex of the universe's outward journey, and the moment gravity becomes the dominant force once more. The transition itself would be imperceptible. On Earth, nothing would appear to change. But across the cosmos, the redshift that has defined our view of the universe would slowly be replaced by a blue shift. Over billions of years, the light from distant galaxies would be compressed to shorter wavelengths as they began to move toward us. The emptying sky of the Big Freeze scenario would be replaced by a sky that grows more crowded and brighter. Galaxies that had receded from view would reappear, growing larger with each passing millennium. As the universe shrinks, the temperature of the cosmic microwave background, the afterglow of the Big Bang, would begin to rise. The space between galaxies would start to glow. The density of matter and energy would increase. Collisions and mergers between galaxies would become common. In the final stages, the background radiation would become hotter than the surfaces of stars. Stars would absorb energy from the space around them, causing them to bloat and destabilize. The universe would become a chaotic, incandescent environment. As the collapse accelerates toward a final singularity, all matter and energy would be drawn together. The universe would end as it began, in a point of unimaginable density and temperature. This is the Big Crunch, a symmetrical reversal of the Big Bang. Some have even speculated that this could lead to a Big Bounce, where the singularity gives rise to a new Big Bang, creating a cyclical universe of endless deaths and rebirths. It is a breathtaking, if entirely speculative, possibility. The ultimate fate of the universe remains one of the most profound open questions in science. For years, the evidence pointed toward a cosmos destined for a cold, quiet end, shaped by the force of dark energy. But the story of science is one of evolution. The latest evidence, while preliminary, suggests a more dynamic narrative. It hints at a universe where the balance of power between cosmic expansion and gravity may be shifting once again. This new work has revived the idea of the Big Crunch, a universe that does not just end, but perhaps begins anew. This does not mean the case is closed. Years of observation and debate lie ahead. What is certain is that we are witnessing a fascinating moment in our journey of understanding. The universe's final chapter is still being written, and the truth is hidden in the nature of the dark energy that permeates the cosmos. The continued study of these immense forces offers valuable insights into the processes that drive evolution on the grandest possible scale. The one thing we know for sure is that the cosmos is far more complex and surprising than we have yet imagined. Scientists just proved the universe is expanding too fast. The James Webb Space Telescope was built to see the unseeable. It's a golden eye designed to peer back to the dawn of time, witnessing the first stars ignite and the first galaxies form. Its job was to answer our biggest questions about where everything came from. But instead of easy answers, it stumbled upon a profound and terrifying contradiction. It has confirmed our worst fears about the universe. The very fabric of spacetime is stretching faster than all of our theories say it should. This isn't a small rounding error. This is a chasm that has opened up at the heart of modern physics. On one side, you have our observations of the universe today. On the other, our predictions based on how the universe began. And they just don't match. For years, scientists hoped it was a mistake, a smudge on the lens, a miscalculation. But with its incredible precision, the Webb telescope has wiped away that hope. It didn't find a flaw, it confirmed the measurements of its predecessor, the Hubble Space Telescope. And in doing so, it has solidified a crisis. The problem isn't our telescopes, it's our understanding of the cosmos itself. We're now facing the real possibility that our entire model of the universe is fundamentally wrong. And solving this might not just tweak our theories, but shatter them entirely. The established truth, a universe in motion. To get why this is a crisis, you first need to get the bedrock of modern cosmology. The universe is expanding. For most of history, we saw the universe as a static, unchanging stage. That all changed in the 1920s, thanks to an astronomer named Edwin Hubble. From his observatory, Hubble was doing something revolutionary, measuring the distances to other galaxies and analyzing their light. He noticed something odd. The light from nearly every galaxy was stretched, shifted toward the red end of the spectrum. This is called redshift, and it's the cosmic version of the Doppler effect. Think of an ambulance siren. As it speeds away, the pitch drops. In the same way, light from an object moving away from us stretches and becomes redder. Hubble realized he was seeing the ambulance siren of the cosmos. Galaxies weren't just sitting there, they were speeding away from us. But the real mind-blowing discovery came when he plotted their speed against their distance. The farther away a galaxy was, the faster it was moving away. This wasn't a chaotic explosion. This was space itself stretching, carrying the galaxies along for the ride. The classic analogy is a loaf of raisin bread baking. You're on one raisin. As the dough expands, every other raisin moves away from you. A nearby raisin moves slowly. A raisin on the far side of the loaf moves much faster, because there's more expanding dough in between. No raisin is the center. Every raisin sees every other raisin moving away. That's our universe. We're on a raisin in an infinitely expanding loaf. This discovery gave birth to the Big Bang Theory. If everything's expanding now, it must have been unbelievably small and dense in the past. To put a number on this expansion, scientists use the Hubble constant, h0. It's one of the most important numbers in cosmology, telling us how fast the universe is expanding today. It's measured in kilometers per second per megaparsec. A megaparsec is just a huge unit of distance, about 3.26 million light-years. So, if h0 is 70, it means for every megaparsec a galaxy is from us, it seems to be moving away 70 kilometers per second faster. Getting this number right is critical. It tells us the expansion rate and helps us calculate the age of the universe. For decades, cosmologists have been trying to nail down this value. And in doing so, they accidentally found a clue that would unravel everything. They discovered that depending on asterisk how you measure it, you get two different answers. And that's not supposed to happen. The incriminating evidence: two detectives, two stories. Imagine two brilliant detectives investigating the same case, the universe's expansion. They use different methods but the same laws of physics. Yet, they come back with two completely different stories. That's exactly what has happened. Our first detective investigates the local, or late, universe. This is like using a radar gun to clock the speed of nearby galaxies. The main technique is called the cosmic distance ladder. Each rung on the ladder lets us measure farther out, with each step calibrated by the one before it. The first rung is parallax. Hold your thumb out and look at it with one eye, then the other. Your thumb appears to jump. That's parallax. Astronomers do the same by measuring a nearby star's position against a distant background, then measuring it again 6 months later when Earth is on the other side of the Sun. This gives them a direct distance. But it only works for nearby stars. To go deeper, we need standard candles, objects with a known brightness. If you know you're looking at a 100-watt bulb, you can tell how far away it is by how dim it appears. In space, our favorite 100-watt bulbs are Cepheid variable stars. These stars pulse, and their pulsation period is directly linked to their true brightness. Find a Cepheid, measure its pulse, and you know how bright it really is. Compare that to how bright it looks, and you can calculate its distance. For the highest rungs, we use an even brighter candle, type Ia supernovae. These are massive star explosions that are incredibly uniform. They all reach almost the same peak brightness. By finding them in distant galaxies, we can measure distances across billions of light-years. This distance ladder method, led by scientists like Nobel laureate Adam Rees, has gotten incredibly precise. When they point their radar gun at the universe today, they consistently get a value of around **73 kilometers per second per megaparsec. The error bars are tiny, so they're very confident in this number. Now for our second detective. This one looks at the early universe using the afterglow of the Big Bang, the cosmic microwave background, or CMB. This is the oldest light in the universe, a snapshot from when it was just 380,000 years old. At that time, the universe cooled enough for atoms to form, and light was set free. Today, we see this light as a faint microwave glow from every direction. It's almost perfectly uniform, but it has tiny temperature ripples. These ripples were the seeds of all future structures, where gravity would eventually form stars and galaxies. And they contain a treasured trove of information. Using our standard model of cosmology, called lambda-CDM, scientists can take this baby picture of the universe, run the clock forward 13.8 billion years, and predict what the expansion rate should be today. And here's the crisis. The prediction from the early universe, measured by experiments like the Planck satellite and confirmed by the Atacama Cosmology Telescope, gives a Hubble constant of about **67 kilometers per second per megaparsec. So, detective number 1 measures the universe today and gets **73. Detective number 2 uses a picture of the baby universe and our best theory to predict it should be **67. For years, everyone hoped their uncertainties would overlap. But as our measurements got better, the error bars shrank. Now, they don't touch. The discrepancy is real. One of them, or both, must be wrong. The contradiction, when precision creates a crisis. This gap between 67 and 73 is what astronomers call the Hubble tension. A difference of 6 might not sound like much, but in precision science, it's a gaping chasm. Something is fundamentally broken. For a long time, the best guess was a subtle error in the distance ladder method. Maybe stellar crowding was throwing off the Cepheid measurements, making them seem closer than they were and inflating the result. This is where the James Webb Space Telescope came in. With its incredible sharpness, it could reobserve these Cepheids and check Hubble's work. The hope was that JWST would find the error, the local measurement would drop from 73 towards 67, and the crisis would be over. In early 2024, the results came in, and they did the exact opposite. JWST's ultra-precise data confirmed Hubble's measurements. It showed that the old data was right all along. Instead of closing the gap, JWST slammed the door on the idea that it was all just a measurement error. The local value is firmly at 73. As Adam Rees put it, the discrepancy suggests our understanding of the universe may be incomplete. With both of NASA's flagship telescopes now in agreement, the problem isn't our tools. The contradiction is baked into the cosmos. This forces us to face a wild possibility. If the measurements are right, the theory connecting them must be wrong. That theory, the lambda-CDM model, has been the foundation of cosmology for decades. It explains almost everything we see, yet it can't reconcile these two numbers. The Hubble tension is now a direct challenge to our entire story of the universe. Something is missing. The investigation, in search of new physics. With measurement error mostly off the table, the investigation has turned to a much more thrilling possibility: new physics. The Hubble tension isn't a problem anymore, it's a clue. It's a giant arrow pointing to a crack in our standard model, and through that crack, we might find a whole new understanding of the universe. One of the lead suspects is dark energy. In our standard model, we assume it's constant. But what if it isn't? A theory called early dark energy suggests that a new energy field gave the universe an extra kick shortly after the Big Bang, then vanished. This would have sped up the early expansion in a way our models don't account for, leading to the higher value we measure today. Another suspect is dark matter. We call it cold and assume it only interacts with gravity. But what if it has other, richer properties? What if it can interact in some small way with light or other particles? That would change the recipe of the early universe and alter the prediction from the CMB. A third idea is a new particle. Some theories suggest a sterile neutrino, a ghostly particle that only interacts with gravity. Adding a new particle to the early universe would change its energy balance and affect the expansion rate. Or, in the most radical idea, maybe Einstein's theory of gravity itself is incomplete on cosmic scales. This is a dangerous path, since general relativity has passed every test we've thrown at it for over a century, but a crisis this deep means everything is on the table. To help settle the debate, scientists are turning to a third detective: gravitational lensing. Massive galaxies can act like cosmic magnifying glasses, bending the light from an object like a quasar behind them and creating multiple images. Since the light from each image takes a different path, it arrives at Earth at a slightly different time. By measuring this time delay, astronomers can calculate the Hubble constant in a completely independent way. So, what does this new detective say? The latest results, from collaborations like TDCOSMO, are fascinating. Their measurements are pointing to a higher value for the Hubble constant, around 73 or 74 kilometers per second, (mpc), in strong agreement with the late universe value from supernovae. This strengthens the case that the problem isn't with the measurements of today's universe, but with our predictions from the past. This whole field is in a state of thrilling upheaval, a mystery unfolding in real time. But this isn't just about numbers. It's about our cosmic story. Are we missing a chapter from the beginning of time? Do we need to rethink the dark energy and dark matter that rule the cosmos? The frontier of science. The James Webb Space Telescope went looking for clarity and came back with a beautiful, profound mystery. It confirmed that the universe is expanding faster than our best theory says it should. But this isn't a failure. This is what science looks like. A crisis doesn't mean science is broken. It means we're on the verge of a breakthrough. Every great leap forward was born from a moment when the data refused to fit the theory. The Hubble tension is the crisis of our time. It has challenged an entire generation of scientists. The standard model of cosmology, a monumental achievement, is showing its cracks. And through those cracks, we are getting a glimpse of a new, undiscovered landscape of physics. The hunt is on. Scientists are racing to find the signature of early dark energy or evidence for new particles. All eyes are on the next generation of observatories. The Nancy Grace Roman Space Telescope will discover hundreds of thousands of new supernovae, while ground-based telescopes will map the sky with incredible depth. We live in a privileged moment. We're the first generation to know the age of our universe and to have a picture of its infancy. But we might also be the last generation to believe that our current model of the cosmos is the final word. The universe has proven to be more complex and more mysterious than we ever imagined. The solution to the Hubble tension won't just be a new number. It will be a new chapter in our cosmic story, and maybe a completely new understanding of reality itself. The universe is expanding too fast, and the race to find out why is the most exciting journey in all of science. The great cosmic debate is the universe expanding or not. For almost 100 years, we thought we had it figured out. The universe is expanding. Then, for the last 25 years or so, we've been told a dramatic, Nobel Prize-winning story about a mysterious force called dark energy that's flooring the cosmic accelerator, pushing everything toward a cold, lonely future. It's a story that has literally defined modern science. But what if that story is wrong? What if the fundamental measurements that built this entire idea were built on a mistake? And what if new evidence shows the most powerful force in the cosmos is actually losing its grip? The fate of reality is hanging in the balance. The story of our beginning and our ultimate end is being rewritten right now. We are in the middle of the great cosmic debate. Is the universe's expansion speeding up, or is it, against all odds, starting to slow down? The expanding canvas and the force of gravity. To really get what this debate is all about, we need to rewind the clock. Picture it, 1929. At the Mount Wilson Observatory in California, an astronomer named Edwin Hubble makes a discovery that changes humanity's place in the universe forever. We used to think our Milky Way galaxy was it, the whole cosmic shebang. But Hubble, using the best telescope of his day, looked at these faint, fuzzy lights everyone called spiral nebulae. He measured how far away they were and how fast they were moving, and what he found was stunning. These weren't just clouds in our galaxy, they were entire galaxies themselves, millions of light years away. And here's the kicker. Almost all of them were flying away from us. The farther out a galaxy was, the faster it was receding. This wasn't some chaotic explosion in a fixed, empty box. This was the fabric of space itself stretching out, carrying all the galaxies along for the ride. The classic way to picture this is the raisin bread analogy. Think of a loaf of unbaked dough with raisins scattered inside. As that dough bakes and expands, every raisin moves away from every other raisin. From the perspective of any one raisin, all the others look like they're speeding away. The raisins aren't moving through the dough. The dough between them is expanding. The raisins are galaxies, and the dough is spacetime. Hubble proved we live in a dynamic, expanding universe. This was a pillar of modern cosmology, but it led to a huge question. If everything is expanding, what happens next? There's one force that should be running the show on this scale: gravity. Gravity pulls everything together. Every star, every planet, every galaxy is tugging on everything else. So, for decades after the Big Bang, scientists assumed the story went like this. The initial push from the Big Bang was going out, but the combined gravitational pull of all the stuff in the universe was acting like a giant cosmic brake. The expansion had to be slowing down. The only question was by how much. This led to three possible endings for the universe's story. First, the Big Crunch. If there was enough stuff, enough matter and therefore enough gravity, the expansion would slow down, stop, and then reverse. Galaxies would come crashing back together, getting hotter and hotter, until everything collapsed into a single, fiery point. Second, the Big Freeze. If there wasn't enough matter, gravity would be too weak to stop the train. The universe would expand forever, but slower and slower over time. Galaxies would drift apart, stars would burn out, and the cosmos would become a cold, dark, and empty void. And third, the Goldilocks option. If the amount of matter was just right, the universe would expand forever, with the expansion rate getting closer and closer to zero but never quite reaching it. For most of the 20th century, this was the debate. Astronomers pointed their telescopes at the sky, trying to weigh the universe to figure out if our fate was fire or ice. They were all looking for signs of a slowdown. Nobody was ready for what they actually found. The Great Shock of 1998. At the tail end of the 20th century, cosmology got hit with a bombshell. A discovery so wild it didn't just answer the question of the universe's fate. It turned physics on its head. And it all came from watching stars blow up. Specifically, Type Ia supernovae. A Type Ia supernova is a special kind of explosion. It happens when a white dwarf star, the super-dense corpse of a star like our Sun, is in a binary pair. This white dwarf is like a cosmic vampire, sucking material off its partner star. It keeps getting heavier and heavier until it hits a very specific weight limit. About 1.4 times the mass of our Sun, known as the Chandrasekhar limit. At that exact point, the core ignites in a runaway thermonuclear reaction, and the star goes kaboom. It's an explosion so bright it can outshine its entire galaxy. Because they all explode at the exact same mass, scientists figured they should all have the same true brightness. They're standard candles. Think of it like this. If you see a row of 100-watt light bulbs trailing off into the distance, you can tell how far away each one is just by how dim it looks. Type Ia supernovae were our cosmic light bulbs. In the 1990s, two rival teams of astronomers set out to use these cosmic light bulbs to measure how much the universe's expansion had slowed down. One was the Supernova Cosmology Project, led by Saul Perlmutter. The other, the High-Z Supernova Search Team, was co-led by Brian Schmidt and Adam Rees. They were hunting for supernovae in galaxies billions of light years away. The work was brutal. They'd take pictures of thousands of galaxies, wait a few weeks, and then take the exact same pictures again. By digitally subtracting the old image from the new one, they could spot the tiny new pinpoint of light from a fresh supernova. When they found one, it was a mad dash to measure its light to confirm it was a Type Ia and track how it faded. They measured its redshift, which told them how fast it was moving away, and its dimness, which told them how far away it was. The goal was to prove the expansion was slowing down. They expected to see that the most distant supernovae were brighter than they should be, a sign that the universe was expanding faster in the past. But that's not what they saw. In 1998, both teams reached the same, staggering conclusion. The distant supernovae weren't brighter. They were dimmer. Consistently, weirdly, dimmer. There was only one way to explain it. The supernovae were farther away than they were supposed to be. And the only way for that to happen was if the expansion of the universe hadn't been slowing down at all. It had been speeding up. For the first 7 or 8 billion years, gravity was winning and the expansion was slowing. But then, something else took over. Some strange, repulsive force started pushing everything apart, faster and faster. The discovery was so huge that the team leaders, Saul Perlmutter, Brian Schmidt, and Adam Rees, would go on to share the 2011 Nobel Prize in Physics for their work. It was like throwing an apple in the air and watching it shoot off into space, faster and faster. It broke all the rules. They had discovered the runaway universe. The rise of dark energy. Okay, so the universe is accelerating. That much was clear. But what was hitting the gas? The answer scientists came up with was basically a placeholder for, we don't know. They called it dark energy. It wasn't a totally new idea. It actually came from what Albert Einstein called his biggest blunder. Back in 1917, Einstein's new theory of general relativity told him the universe should be either expanding or contracting. But the science of his day said the universe was static. So, to make his math work, he added a fudge factor, the cosmological constant. He imagined it as an energy built into empty space itself, a kind of anti-gravity that pushed outward, perfectly balancing gravity to keep the universe still. When Hubble discovered the universe actually was expanding, Einstein dropped the idea. But in 1998, Einstein's blunder made a dramatic comeback. That cosmological constant was the perfect explanation for this mysterious acceleration. Scientists dusted it off and gave it the new, cooler name, dark energy. So what is it? Conceptually, dark energy is the energy of space itself. Even in a total vacuum, quantum mechanics says there's a fizz of virtual particles popping in and out of existence. This gives empty space a baseline energy. And this energy has a weird property, negative pressure. In general relativity, that creates a repulsive force. It pushes things apart. Now, here's the key part. As the universe expands, matter and radiation get spread out and diluted. But the density of dark energy, the energy in each cubic meter of space, stays constant. This set up the ultimate cosmic tug of war. In the early universe, matter was packed tight, so gravity was king. For the first 9 billion years or so, gravity did slow the expansion down, just like everyone expected. But as space kept stretching, the matter spread out, and its gravitational grip got weaker. Dark energy, meanwhile, stayed just as strong. Around 5 to 7 billion years ago, we hit a tipping point. The push of dark energy overpowered the pull of gravity. The cosmic brakes failed, the accelerator hit the floor, and the age of acceleration began. This became the standard model of cosmology, known as the lambda-CDM model. Lambda stands for the cosmological constant, dark energy, and CDM is for cold dark matter. According to this model, dark energy makes up about 70% of the universe. Dark matter is another 25%, and all the normal stuff we see and are made of, stars, planets, you and me, is a measly 5%. We're just the foam on top of a vast, dark ocean. And the fate this model predicted? A pretty bleak one. If dark energy is constant, the universe will accelerate forever into a big freeze. Galaxies will be pushed so far apart that the sky will go dark. Stars will die. The universe will become a cold, empty, and silent void. For over 2 decades, this has been the accepted story. This was the standard story for more than 2 decades, the bedrock of modern cosmology. But the plot is thickening. If you love a good cosmic mystery, make sure you're subscribed and have those notifications turned on, because what comes next changes everything. The plot twist. A crack in the cosmos. The standard model, lambda-CDM, was a huge success. It explained a ton of data and painted a coherent picture of our universe. But good science is all about poking holes in your own theories, and by the 2020s, some serious cracks started to show. The biggest one was called the Hubble tension. Basically, we have 2 main ways to measure how fast the universe is expanding today. When we look at the late universe nearby, using things like supernovae, we get one number, around 73 kilometers per second, MPC. But when we look at the early universe by studying the afterglow of the Big Bang, we get a different, lower number, around 67 kilometers per second, MPC. For years, scientists hoped it was just a measurement error. But the better our instruments got, the worse the tension became. It was a huge hint that our model might be wrong. Then, in late 2025, a research team from Yonsei University in South Korea, led by Professor Young-Wook Lee, published a study that suggested the whole foundation was cracked. They went back to the source, the Type Ia supernovae. For decades, the big assumption was that they were perfect, standard candles. But Lee's team asked a simple, brilliant question. What if the age of the star system affects the explosion? A supernova that goes off in a young, star-forming galaxy might be different from one in an old, red and dead, galaxy. They analyzed over 300 supernovae and found a stunning correlation. Even after all the usual corrections, supernovae from younger star populations were fainter, and those from older populations were brighter. They confirmed this progenitor age bias with a 99.999% confidence level. This was like finding out your trusty meter stick had been secretly changing size all along. The whole discovery of acceleration in 1998 was based on distant supernovae being dimmer than expected. But looking at distant galaxies is looking back in time, to when the universe was younger. What if those distant supernovae weren't dimmer because they were farther away? What if they were dimmer simply because they came from younger stars and were naturally less bright to begin with? The team did the next logical thing. They reanalyzed all the data, but this time, they corrected for the age bias. They recalibrated their cosmic ruler. And when they did, the evidence for acceleration just vanished. In fact, the corrected data showed the opposite. When combined with other cosmic measurements, the team concluded with a mind-blowing 9 sigma statistical significance that the standard lambda-CDM model was wrong. For perspective, 5 sigma is the gold standard for a discovery in physics. 9 sigma is a level of certainty that makes the entire world stop and listen. And the biggest shocker? The new analysis showed the universe is not accelerating today. Dark energy is weakening, and gravity is fighting back. The universe has already switched from accelerating to decelerating. The slowdown has begun. As Professor Lee put it, this could mark a major paradigm shift in cosmology. The cosmic tug-of-war reignited. So, as you can imagine, this Yonsei study has thrown cosmology into chaos, in the best way possible. It suggests dark energy isn't a constant, but a dynamic force that changes over time, something theorists call quintessence. It had its moment of glory, but now it seems to be fading. This is where it gets really interesting. Just a year before, in 2024, another huge project, the Dark Energy Spectroscopic Instrument, DESI, released its own amazing results. They created the biggest 3D map of the universe ever and also found that dark energy seemed to be changing. But they came to a crucially different conclusion. They said, yes, it's weakening, but the universe is still accelerating today, just not as much as before. So who's right? Has the slowdown already started, or is it still in our future? The Yonsei team has a pretty direct answer. They argue the DESI analysis, while amazing, still relied on the old supernova data, the data that hadn't been corrected for that critical age bias they discovered. According to Professor Lee, if you take DESI's own excellent data and combine it with the age-corrected supernova data, the conclusion is clear. Deceleration is happening right now. This is science at its most thrilling. It's not a settled fact from a textbook. It's a live debate happening on the absolute frontier of knowledge. The ultimate fate, fire or ice? And this isn't just some academic squabble. The answer to this question changes the answer to the biggest question of all. How does it all end? For 25 years, the accepted story pointed to a lonely end in a big freeze, or a violent big rip. In the big rip, the acceleration would become so strong it would eventually tear galaxies, planets, and even atoms apart. But if the Yonsei study is right, if dark energy is weakening and gravity is making a comeback, then an old idea, long left for dead, comes roaring back to life. The Big Crunch. If gravity is regaining control, the expansion could eventually stop. And then, there's only one way to go, back down. The universe would start to contract. Galaxies would race toward each other. The cosmos would shrink, getting hotter and denser, until everything was destroyed in a fiery singularity, the Big Bang in reverse. Recent calculations from a Cornell physicist suggest the universe could stop expanding in about 11 billion years and then collapse back in on itself over the next 20 billion. Some even speculate about a big bounce, where that crunch could trigger a new Big Bang, starting a new universe in an endless cycle of cosmic death and rebirth. Suddenly, the cold, empty future has been replaced by a possible hot, fiery end, or maybe a new beginning. So where are we now? We're in the middle of a scientific revolution. A Nobel Prize-winning idea that has defined cosmology for a generation is now on the ropes, challenged by stunning new data. Is dark energy a constant, or is it fading? Is the universe speeding up, as DESI suggested, or is it already slowing down, as the Yonsei team argues? Is our destiny a cold, endless void, or a fiery, cyclical collapse? We don't have the final answer. But all eyes are now turning to a new game-changer, the Vera C. Rubin Observatory in Chile. It began its massive survey in 2025 and will discover tens of thousands of new supernovae. Within the next 5 years, the data from Rubin is expected to give us enough information to settle this debate, once and for all. We are on the verge of either reconfirming our standard model of the universe or watching it crumble, giving way to a new era of cosmology. The great cosmic debate is far from over. What do you think? Are you on Team Big Freeze or Team Big Crunch? Let us know your thoughts in the comments below. And if you want to stay on top of the biggest questions in science, don't forget to like and subscribe for more journeys to the edge of what we know. Cosmology's biggest discovery was just debunked. For more than a quarter of a century, our picture of the universe has included a profound and quiet truth: that the cosmos is not just expanding, but that its expansion is speeding up. This understanding, recognized with a Nobel Prize, became a foundation of modern cosmology. It shaped our view of the universe and our place within it. It suggested that an unseen influence was slowly winning a contest against gravity, pushing everything apart, faster and faster, toward a cold and empty future. But what if this understanding, as fundamental as it seemed, was incomplete? What if the foundation was based on an assumption that needed to be re-examined? In 2025, a series of new results suggested exactly that. The most accepted theory in cosmology is now facing a new challenge, and the story of the universe's ultimate fate is once again open to interpretation. Imagine throwing a ball into the air. You expect it to slow, stop, and return. That is gravity. For most of the 20th century, astronomers believed the universe worked in a similar way. After the initial expansion of the Big Bang, the gravitational pull of all the matter within the cosmos was expected to act as a brake. The expansion, it was assumed, had to be slowing down. The only real question was whether it would slow enough to reverse into a big crunch, or if it would expand forever, but more and more slowly. That was the choice. But the universe, it turned out, was not limited to those two possibilities. The unexpected acceleration. Before 1998, the field of cosmology seemed to be converging on a settled picture. The story of the universe was one of a competition between the outward momentum from the Big Bang and the inward pull of gravity. And gravity, it was thought, would eventually gain the upper hand. To test this idea, to measure precisely how much the expansion was slowing, two independent teams of astronomers began an ambitious project. One was the Supernova Cosmology Project. The other, the High-Z Supernova Search Team. Their plan was both elegant and difficult. It required measuring the distances to the farthest parts of the cosmos and comparing those distances to the speed at which those regions were moving away. To do this, they needed a special kind of cosmic measuring tool, something called a standard candle. Think of it this way: if you see a car's headlights in the dark, you can guess its distance. The dimmer the lights appear, the farther away the car is. This works because you have an intuitive understanding of how bright headlights are supposed to be. In cosmology, a standard candle is an object whose true, or intrinsic, brightness is known. If you know how bright something really is, you can determine its distance by measuring how dim it appears. For this purpose, astronomers use a specific kind of stellar explosion, a type Ia supernova. They occur when a white dwarf star in a binary system pulls too much matter from its companion, exceeds a critical mass, and triggers a thermonuclear explosion. Because they all ignite at roughly the same mass, they reach a similar peak brightness. This makes them reliable tools for measuring vast cosmic distances. Find a type Ia supernova, measure its apparent dimness, and you can calculate how far away its host galaxy is. So, these two teams spent years at the world's most powerful telescopes, watching small patches of the night sky. They were looking for these brief explosions in galaxies billions of light years away. For each one they found, they also measured its redshift, the stretching of its light caused by the expansion of space. Redshift tells you how much the universe has expanded since the light left the supernova. It tells you how far back in time you are looking. Their mission was to create a map of how the universe's expansion had changed over time. The expectation was clear. The most distant supernovae, which exploded when the universe was younger, should appear to be moving away faster than a simple constant expansion would suggest. This is because gravity would not have had as much time to slow things down back then. They were setting out to measure a deceleration. But when the data arrived, it showed something else entirely. It was the opposite of what was expected. The most distant supernovae were not brighter than predicted, they were dimmer. The implication was difficult to accept. For these standard candles to appear dimmer, they had to be farther away than the existing models allowed. And for them to be farther away, the expansion of the universe could not have been slowing down. At some point in the last several billion years, it must have begun to speed up. The researchers spent months searching for other explanations. Perhaps dust was obscuring the light, making the supernovae seem dimmer. Or perhaps ancient supernovae were chemically different from those seen today. They checked every possibility. The other team, working independently, was going through the same process of careful doubt. Yet both arrived at the same conclusion. The expansion of the universe is accelerating. It was a discovery that changed cosmology. To explain it, scientists revisited an idea Albert Einstein had once called his biggest blunder, the cosmological constant. Represented by the Greek letter lambda, it was a term Einstein had added to his equations to counteract gravity and keep the universe static. When it was discovered that the universe was expanding, he removed it. But now it returned, rebranded as dark energy. This cosmological constant could be seen as an energy inherent to space itself, a kind of background pressure pushing everything apart. As the universe expands, the density of matter thins out, and gravity's influence weakens over large distances. But the density of dark energy, being a property of space itself, remains constant. As more space is created, more of this energy appears with it. According to this model, about 5 billion years ago, the repulsive force of dark energy finally overtook the attractive force of gravity, and the era of acceleration began. This new picture was formalized in what is known as the lambda-CDM model, lambda for dark energy and CDM for cold dark matter. A universe made of about 5% ordinary matter, 25% dark matter, and 70% dark energy. This model was very successful, explaining not only the supernova data but also the large-scale structure of the cosmos. For their work, the leaders of the two teams were awarded the 2011 Nobel Prize in Physics. The accelerating, dark energy-dominated universe became the standard model. The story seemed to be written. The universe was destined to expand forever, faster and faster, until every other galaxy is pulled beyond our horizon, leaving our own in a quiet, isolated void. A new perspective. For 27 years, the lambda-CDM model has been the bedrock of cosmology. There were some unresolved questions, like a disagreement over the precise value of the universe's current expansion rate, a problem known as the Hubble tension. But these were often seen as details that would be resolved with better measurements or minor adjustments to the model. The core idea of an accelerating expansion driven by a constant dark energy was widely accepted. But science is a process of continual refinement. While the model became textbook knowledge, a new generation of instruments was built. The most powerful of these is the Dark Energy Spectroscopic Instrument, or DESI. From its position on Kitt Peak in Arizona, DESI uses 5,000 robotic fiber optic positioners, each one able to fix onto a distant galaxy and capture its light. It is creating the largest 3D map of the universe ever attempted, charting tens of millions of galaxies over 11 billion years of cosmic time. As DESI began releasing its data in the mid-2020s, it confirmed the standard picture with remarkable precision. But it also contained hints of something unexpected. Some early DESI results suggested that dark energy might not be constant, but could be weakening over time. It was a team from Yonsei University in South Korea, however, that proposed a more fundamental revision. The team, led by Professor Young-Wook Lee, decided to re-examine the foundation of the 1998 discovery, the Type Ia supernovae themselves. The theory of an accelerating universe depends on the assumption that these supernovae are truly standard candles, that a supernova from 7 billion years ago had the same intrinsic brightness as one from today. But what if this assumption was not entirely correct? The Yonsei team suggested a new kind of systematic effect they call progenitor age bias. The idea is that the brightness of a supernova might depend on the age of the stars that create it. A supernova that occurs in an old, elliptical galaxy comes from a stellar population that is billions of years older than one in a young, star-forming galaxy. These different environments could subtly alter the explosion. When the team analyzed a large sample of supernova host galaxies, they found a strong correlation. Even after standard corrections, supernovae from younger stellar populations appeared systematically dimmer, while those from older populations appeared systematically brighter. This presents a quiet but profound problem. As we look farther away in the cosmos, we are also looking back in time. Distant galaxies are, on average, younger than nearby galaxies. This means the most distant supernovae used in the original 1998 studies tended to come from younger star systems. And according to the Yonsei team's findings, these younger supernovae might be intrinsically dimmer. Suddenly, the dimness of those distant supernovae had a potential new explanation. Perhaps they looked dimmer not because of cosmic acceleration, but because they were a naturally dimmer type of supernova. The effect might be a matter of stellar astrophysics, not cosmology. The team then did the next logical step. They calculated a correction for this age bias and applied it to existing supernova data. When they did, the picture of the universe changed. The evidence for cosmic acceleration was no longer present. When they combined their age-corrected supernova data with other cosmological measurements, such as the baryon acoustic oscillations, BAO, from Daisy, which act as a standard ruler, their results suggested something even more significant. Their analysis indicated that the universe is not accelerating today. Instead, it may have already entered a phase of decelerated expansion. The cosmic brakes, it seems, might be on again. This is where the scientific process is now at work. The main Daisy collaboration, using much of the same data but without this specific age bias correction, reached a more moderate conclusion. Their results also suggest dark energy might be weakening, but they find the universe is still accelerating at present. The discussion now centers on this crucial point: how to correctly interpret the brightness of supernovae. The Yonsei team argues their correction brings the standard candle measurements into better agreement with the standard ruler measurements. But in doing so, it removes the need for present-day cosmic acceleration. It is a fundamental question about how to read our best cosmic data, and the outcome could reshape our understanding of the universe. An evolving cosmos. What does it mean if this new interpretation is correct? If dark energy is not a constant, and the universe is already beginning to slow down, it means we may need to explore a more dynamic cosmos. This new evidence points toward a concept called evolving dark energy, or quintessence. Unlike the cosmological constant, the strength of this energy field would change over cosmic time. For billions of years, it was strong enough to drive acceleration, but now its influence may be waning, allowing gravity to slowly regain its dominant role. This idea that dark energy evolves could help with other puzzles in cosmology. For one, it might help resolve the Hubble tension by changing the expansion history of the universe in a way that could bring measurements from the early and late cosmos into closer agreement. A fascinating, though still speculative, idea is the cosmologically coupled black hole, or CCBH model. This hypothesis proposes that black holes themselves could be the source of dark energy. In this view, when a massive star collapses, the matter of the star is converted into dark energy. The amount of dark energy in the universe would not be a fixed number, but would grow over time, connected to the history of star formation. The Daisy data itself shows tantalizing hints that the dark energy density seems to track the rate of star formation, lending some support to this idea. This new picture also completely reimagines the ultimate fate of the universe. The lambda CDM model, with its constant dark energy, pointed to a big freeze, where the universe would expand exponentially forever until only a cold, empty void remained. But if dark energy is weakening, the future is unwritten. A slowing expansion could mean the universe gently expands into infinity, its light slowly dimming. Or, if the dark energy weakens enough, gravity could eventually become dominant again on a cosmic scale. The expansion could one day halt and reverse, leading to a big crunch, where the universe collapses back into a single point, perhaps even triggering a new Big Bang in a cyclical process. The old questions are once again open for debate. This discussion, between a constant dark energy and an evolving one, between a universe that is accelerating and one that may be slowing down, is happening right now at the cutting edge of cosmology. What we've talked about today is not a final conclusion, it is a scientific conversation in progress. If this kind of calm exploration of our universe is something you find valuable, consider subscribing to the channel. So, where does this leave us? For 27 years, we have had an answer for one of the most fundamental questions. What is the fate of our universe? The answer was one of endless, accelerating expansion into emptiness. The 1998 discovery of cosmic acceleration was a monumental achievement, a pillar of modern science. And now, that pillar is being carefully re-examined. The work from Professor Young-Wook Lee's team, combined with the data from Daisy, has presented cosmology with a new possibility. That our understanding was incomplete, biased by an assumption we did not know we had to question. This is not a failure of science. This is science. It is the process working as it should, with better data and new ideas challenging even our most deeply held conclusions. A Nobel Prize does not grant a theory immunity from revision. It marks our best understanding at a particular time. And our understanding can change. This story is one of progress, of peeling back a layer of reality to find a more complex and subtle truth underneath. We have journeyed from a universe thought to be ruled only by gravity to one dominated by a mysterious anti-gravity, and now, we may be entering an era of a dynamic, evolving universe, where the cosmic contest is far from over. The revelation of 1998 was that the universe's expansion was speeding up. The potential revolution of 2025 is that it may now be slowing down. We thought we had read the final chapter of the cosmic story. It turns out, we may have just finished the prologue. The universe is once again more mysterious, more complex, and more interesting than we had imagined. The biggest questions are once again open, and the ultimate fate of everything remains beautifully unknown. This new study reveals the universe's expiration date. For a long time, the story of how the universe will end seemed settled. We looked out into the darkness, comforted by a vision of eternity. A universe that would expand forever. A quiet, majestic dance of galaxies drifting slowly apart into an endless, tranquil night. The story was called the Big Freeze, a future of infinite cold and darkness where the cosmos would fade out gently over trillions of years. It was a lonely final chapter, but a peaceful one. But what if that story, which has guided our understanding for decades, was built on an idea that might be incomplete? What if the end is not a slow fade into darkness, but a gradual return to the beginning? A new study, from a team of researchers at Cornell University, has quietly suggested that the ending might be different. It offers evidence that the universe may not have an infinite future, but an expiration date. A final moment where everything we know, and everything we are, is undone. This research looks at the fabric of spacetime and suggests the expansion we have observed for 100 years might not be a one-way journey. It may only be a temporary phase. In this new telling, the universe is like a rubber band that has been stretched near its limit, and we could be approaching the moment it begins to shrink back. The findings, which are currently awaiting peer review, put a number on our cosmic lifespan, predicting a total collapse back in on itself. A big crunch. This idea does not just adjust our theories, it changes the story entirely. It asks us to consider a destiny that is more dramatic, more finite, and perhaps more profound than we had imagined. The era of eternal expansion may be over. The countdown to the end of everything may have already begun. The established story, a universe fated to freeze. To understand how significant this new idea is, we have to travel back and appreciate the story it seeks to revise. For decades, the scientific consensus on the universe's fate was a tale of magnificent, unending loneliness. It was known as the Big Freeze, the Big Chill, or the heat death of the universe. This was not just a guess, it was the logical conclusion drawn from nearly a century of careful observation. The story starts in the early 20th century. The common view, held even by Albert Einstein, was of a static, unchanging cosmos. His own theory of general relativity, published in 1916, first suggested a dynamic universe, one that should either be expanding or contracting under its own gravity. Unsettled by this, he added a cosmological constant to his equations to hold gravity back and keep the universe in a perfect, timeless balance. But the universe had other plans. In the 1920s, astronomers like Edwin Hubble showed that distant galaxies were moving away from us. And the farther away they were, the faster they were receding. This was the first real evidence that our universe was not static, it was expanding. The comfortable, eternal stage was suddenly an evolving place. Einstein would later call his constant his greatest blunder, as the expansion he had tried to erase from his theory was, in fact, reality. For the next 70 years, the crucial question remained: what would happen next? The fate of the cosmos was seen as a quiet contest between two forces. On one side, the momentum of the Big Bang pushed everything outward. On the other, the steady pull of gravity from all the matter in the universe tugged everything back together. The outcome depended on a single factor: how much matter the universe contained. If there was enough, gravity would eventually win. The expansion would slow, stop, and then reverse into a final, big crunch. If not, the expansion would continue forever. Then came the 1990s and a discovery that introduced a new mystery. Two teams of astronomers were using distant stellar explosions, called Type Ia supernovae, to measure the history of cosmic expansion. They expected to find the expansion slowing down. They found the exact opposite. It was speeding up. This discovery was deeply unsettling. It was as if you threw an apple into the air and it shot upwards, faster and faster. Something was pushing the universe apart, overpowering gravity. Scientists gave this mysterious force a name: dark energy. And in a moment of quiet irony, the best way to describe this force was to bring back Einstein's greatest blunder, the cosmological constant, now reimagined as the energy of empty space itself. This discovery seemed to cement the universe's fate. If an anti-gravitational force was dominant, a big crunch was impossible. Gravity had lost the contest. The universe was doomed not to a fiery collapse, but to an endless, accelerating expansion. This led directly to the Big Freeze scenario. The forecast was bleak, stretched over unimaginable time. As galaxies accelerated away, our own local group would become an isolated island in a vast, empty void. In a few 100 billion years, the light from all other galaxies would be gone from our sky. Over trillions of years, the fuel for making stars would run out. The stars would die, one by one, leaving behind a silent graveyard of black holes and cold, dead stellar remnants. Eventually, after a time so long it loses meaning, even the last black holes would evaporate. The universe would be left as a featureless soup of stray particles, approaching a state of maximum entropy known as heat death. The temperature would be almost absolute zero. Time itself would become meaningless, as all change would cease. The cosmos would end not with a bang, but with the quietest silence imaginable. This was the established story. The cold, lonely fate that science had predicted for us. Until now. A shift in the cosmic story, the 2026 Cornell study. Just as we had settled into this long, cold cosmic forecast, a paper appeared in early 2026 that sent a quiet ripple through the world of physics. Authored by a team at Cornell University, it presented a radical re-evaluation of our cosmic destiny. It claimed that the universe is not expanding forever. In fact, it may be nearing the halfway point of its total life, destined to collapse in a big crunch. This wasn't just a new interpretation of old data. The team's conclusion came from a fresh look at findings from two of the world's most advanced observatories, the Dark Energy Survey and the Dark Energy Spectroscopic Instrument. These projects have spent years carefully mapping the cosmos to measure the history of cosmic expansion. Their goal was to understand the exact nature of dark energy. Is it constant, or does it change over time? For 2 decades, our standard model of cosmology has been built on the assumption that dark energy is constant. But the latest data hinted at something else. When analyzed, the results from these two observatories showed a surprising consistency. The data suggested that dark energy might not be constant. It seems to be evolving. This is where the Cornell study made its leap. The researchers proposed a new model to explain this evolution, one that rests on 2 key ideas. First, they suggest that the accelerated expansion we see today is the temporary effect of a hypothetical, ultralight particle. Think of it like a car with its accelerator gently pressed down. This particle field provides the push, causing the universe to expand faster and faster. This part of the theory fits well with what astronomers have observed. But, and this is the crucial twist, the model introduces a second, underlying component. A true, fundamental cosmological constant that is small and negative. A negative constant doesn't push things apart, it pulls them together. It acts like an invisible tension in spacetime, a cosmic rubber band waiting to contract. For the first part of the universe's life, its effect is completely hidden by the powerful, expansionary push of the particle field. But that push is not constant. As the particle field evolves, its energy slowly weakens. The foot is gradually being lifted from the accelerator. Meanwhile, the negative constant, the underlying pull, remains unchanged. It has always been there, a quiet force waiting for its moment. According to the team's calculations, the scales will tip in the future. They predict that the expansion of the universe will continue for approximately another 11 billion years. At that moment, a turning point in cosmic history will be reached. The weakening push will finally become equal to the persistent pull. The acceleration will stop. The expansion will halt. For a fleeting cosmic instant, the universe will be perfectly balanced. And then, the balance will break. The negative constant will become the dominant force. From that point forward, the universe will begin to contract. The cosmic rubber band will snap back. The model provides a specific and shockingly finite timeline. After halting its expansion, the universe will undergo a period of collapse lasting roughly 9 billion years. Adding this to its current age and the period of future expansion, the study places the total lifespan of the universe at approximately 33 billion years. If this model is correct, we are living just past the halfway point of all cosmic history. The eternal, frozen future has been replaced by a definitive end date, a final event now just under 20 billion years away. The quiet, cold whimper of the Big Freeze has been replaced by the possibility of a fiery return to the beginning. What this means for reality. The conclusions of the Cornell study are so profound they ask us to completely reimagine the future. If the universe is destined not for an infinite expansion but for a finite collapse, the implications are deeply philosophical. It changes the nature of our cosmic story. The journey towards the Big Crunch would be, in many ways, the history of the universe played in reverse. The first signs of change would be subtle. For 11 billion years, the universe would keep expanding. Then comes the turning point. The expansion stops. What happens next is a slow but steady process of contraction. Galaxies that were speeding away from us would halt, then begin to move towards us. The redshift of their light, the very evidence of expansion, would slowly diminish and become blue-shifted as they accelerate toward us. The night sky would begin to change in a profound way. For eons, we have looked out into a sky that grows darker and emptier. In a contracting universe, the opposite would be true. Distant galaxies would grow larger and brighter. The sky would become increasingly crowded with light. As the collapse accelerates, the universe would get smaller, denser, and hotter. The cosmic microwave background, the faint, cold afterglow of the Big Bang, would be blue-shifted to higher energies. The empty space between galaxies would begin to glow, first red, then a brilliant white. The idea of night would vanish. The entire sky would blaze with the light of a star's surface. In the final stages, the familiar structures of the cosmos would begin to unwind. Galaxy clusters would rush together and merge. Then, galaxies themselves would collide. Stars would be pulled from their orbits into a chaotic cosmic furnace. The rising temperature of space itself would eventually become so hot it would cook the stars from the outside in. Finally, in an event that defies our comprehension, all matter, energy, space, and time would collapse back into an infinitely dense, infinitely hot singularity, the very same state from which the universe is thought to have emerged. The story of our universe would end not in a cold void, but in a return to the same state in which it began. This destiny raises deep questions. A universe with a definite end feels fundamentally different from one that is eternal. A finite cosmos with a 33 billion-year lifespan transforms our existence into a temporary phenomenon. It gives the cosmos a life cycle, a birth, a life, and a death. Our 13.8 billion-year-old universe is no longer ancient, it's middle-aged. This idea also resurrects a tantalizing theory, the cyclic universe. Some have proposed models where the end is also a beginning. In these Big Bounce scenarios, the singularity of the Big Crunch is not an absolute end but a point of transition, triggering a new Big Bang. Our existence might not be a one-time event, but one chapter in an endless cycle of cosmic birth, death, and rebirth. While the Cornell model doesn't predict what happens after the crunch, it makes such speculation scientifically relevant once again. In this new telling, the cosmos has a dramatic narrative arc. It is a story of explosive creation, a long expansion, a momentous turning point, and a fiery, spectacular end. A quiet cosmic debate. It is important to understand that this prophecy of a big crunch is far from settled science. The Cornell study is a provocative new idea, and the scientific community remains rightly cautious. The announcement has begun one of the most exciting and fundamental debates in modern physics. Will the universe end in fire or in ice? On one side of this quiet debate are the decades of careful work that built our current understanding, the lambda-CDM model. This model, with its constant dark energy and eternal expansion, is the product of overwhelming evidence from many sources: the cosmic microwave background, the large-scale distribution of galaxies, and the original supernova data. The Big Freeze is the deeply entrenched, evidence-backed story. Cosmologists defending this view urge caution. They argue that the hints of evolving dark energy in the new data, while interesting, are not yet strong enough to overturn a theory that has been so successful. Science has a high bar for extraordinary claims, and there is always the possibility of subtle errors in the data or its interpretation that we do not yet see. The simpler explanation, they contend, is that dark energy is what it has appeared to be all along: a simple, unchanging constant. However, the Cornell study is not the only voice questioning eternal expansion. There are other whispers, too, that our understanding might be incomplete. For years, there has been a persistent question known as the Hubble tension. a frustrating disagreement between different methods of measuring the universe's current expansion rate. This tension might be a sign of a flaw in our measurements, or it could be the first real crack in our standard model. An evolving dark energy, like that proposed in the Cornell model, is one of the leading ideas for resolving this tension. This is where cosmology is today, a field in a state of quiet ferment. The old consensus is being questioned, but the new theories have not yet met the high burden of proof needed for a scientific revolution. We are at a genuine crossroads, and the path forward will be paved with more data. Fortunately, a new generation of powerful observatories is already at work. The Euclid Space Telescope and NASA's Nancy Grace Roman Space Telescope are creating vast new maps of the cosmos to study dark energy with incredible precision. And the Vera C. Rubin Observatory in Chile will photograph the entire southern sky every few nights for a decade, cataloging billions of galaxies. The sheer amount of data from these instruments will provide the definitive test. Within the next decade, these observatories will tell us whether dark energy is constant or if it is evolving. They will confirm or refute the claims of the Cornell study. They will determine whether the hints of a coming collapse are the first signs of a new reality, or just a phantom in the data. The scientific process is working as it should. A bold new idea has been proposed, it has spurred a quiet debate, and now it will be tested. The fate of the universe hangs in the balance, waiting for the verdict. We stand at a remarkable moment. For 20 years, we have lived with the scientific story of a universe destined for infinite expansion and cold, lonely darkness. Now, a new study has challenged that certainty, presenting a compelling alternative. A universe with a finite life, returning to its own beginning in less than 20 billion years. We have journeyed from the established story of an eternal cosmos to the quiet reveal of its potential collapse. We have explored what a finite universe might mean, a reality that ends not with a whimper, but with a fire that mirrors its own creation. And we have seen that this new vision is at the heart of a quiet scientific debate, a cosmic mystery that the next generation of telescopes is poised to solve. There is something quietly humbling about this possibility. The conflict between the Big Freeze and the Big Crunch touches upon our most fundamental questions. Does the cosmos have a narrative arc? Is our existence a singular, fleeting event, or part of a grand, endless cycle? For the first time, these are not just questions for philosophy, but questions that science has a real chance of answering. The coming years will be a golden age for cosmology. As data comes in, we will watch this story unfold. We will learn whether we are living in the middle of a finite story or at the beginning of an infinite one. Does this possibility of a finite end change how you see our place in the cosmos? Does it make our brief moment feel more precious or more fleeting? If you want to stay connected to the science that is redefining our universe, consider subscribing to the channel. The story of the cosmos is far from over, and you won't want to miss the next chapter. The cosmic stalemate that could freeze reality forever. Our story, the story of everything, begins in motion. For 13.8 billion years, the universe has been a place of quiet, constant change. From a moment of unimaginable heat and density, it has expanded and cooled, slowly arranging itself into the web of galaxies we see today. We have always assumed this story must have an ending. For generations, we have told ourselves there are only two ways it could conclude. A universe that collapses back on itself in a final, quiet fire. Or one that expands forever, until it becomes a cold, dark, and impossibly empty place. It has always felt like a choice between two kinds of endings. One of fire, the other of ice. But what if there is a third, stranger possibility? A future where the universe does not die, but simply stops. What if the long contest between the gravity pulling everything together and the strange energy pushing it all apart ends not in a victory, but in a perfect, eternal stillness? This is the story of a cosmic stalemate, a theoretical ending that could lock reality into a single, unchanging moment. It is the story of how the universe might not end with a cataclysm or a fade, but with a profound and absolute silence. The two familiar endings. To understand this third, quieter path, it helps to first walk through the two futures that have shaped our picture of the end for a century. Both begin with a single observation made by Edwin Hubble in the 1920s. The universe is expanding. He saw that distant galaxies are moving away from us, and the farther away they are, the faster they go. The common analogy is to imagine living on the surface of an inflating balloon. Every point moves away from every other point, but there is no center. We are not in a special place. The expansion is happening everywhere. This discovery changed our understanding of everything. It meant the universe had a beginning, and it implied it must also have a fate. That fate, physicists realized, was governed by a quiet battle on the largest scale imaginable. On one side is gravity. It is the collective pull of every star, every galaxy, and every particle of dust in the cosmos. Gravity is a force of order and structure, pulling matter together, always trying to gently rein in the expansion. On the other side is a force we know very little about. We call it dark energy. It was discovered in the late 1990s, when astronomers saw that the expansion of the universe was not slowing down as expected. It was speeding up. Something was acting like a kind of anti-gravity, pushing space apart. This quiet pressure now makes up nearly 70% of the universe, and yet we do not know what it is. It remains one of the greatest mysteries in science. The final story of the universe seems to rest on the outcome of this contest between gravity and dark energy. For a long time, this left us with two doors, two possible last chapters. The first is the future where gravity slowly loses and dark energy wins. This is known as the Big Freeze, or the heat death of the universe. In this story, the accelerating expansion never stops. Over trillions of years, galaxies would be pushed so far apart that the light from one could never reach another. The night sky would grow empty, leaving only the stars of our own galaxy in an endless darkness. The universe beyond our local neighborhood would disappear from view. The journey into this cold future is a long one. Star formation would eventually stop. The last stars would flicker out after trillions of years, and the universe would enter an age of darkness. All that would be left are the remains of stars, black holes, neutron stars, and cold white dwarfs. And even these are not forever. Over unimaginable lengths of time, it's thought that matter itself might dissolve, and even the largest black holes will evaporate through a process called Hawking radiation. What remains is a universe that is, for all purposes, empty. A cold, dark, and uniform place where time itself almost loses meaning, because nothing ever happens. For many years, this has seemed the most likely end. But there is another door. A more sudden end, where gravity wins. This is the big crunch. In this version of the future, the universe has enough matter and energy that its gravity is strong enough to one day halt the expansion and reverse it. The cosmic story would begin to play in reverse. Galaxies would come rushing back toward each other. The faint afterglow of the Big Bang, the cosmic microwave background, would grow warmer and brighter. First, it would become too hot for planets, then for stars. In the final moments, the whole sky would be brighter than a star as galaxies merge. The universe would become a furnace, breaking atoms apart, before everything is drawn back into a single, hot, dense point, perhaps beginning a new cycle. This idea of a fiery end was a strong possibility for much of the 20th century, but it seemed less likely after the discovery of dark energy. How could gravity win when a mysterious force was pushing everything apart? For decades, these were the two choices: an endless winter or a final fire. An eternity of cold or a moment of heat. But science is a story of revision. And recent hints from our deepest cosmic surveys suggest the story of the end might be stranger than we thought. The razor's edge. The path to this third, stranger fate begins with a single number. A parameter that describes the overall shape of our universe, which cosmologists call omega. It is a measure of all the matter and energy in the universe, compared to a specific, critical, density. This value is the precise amount of density needed to stop the cosmic expansion after an infinite amount of time. It is a fork in the road. If the universe's density is greater than the critical density, omega is greater than 1, and the universe is closed. Its gravity is strong enough to curve space back on itself, like a sphere, and it will end in a big crunch. If the density is less than the critical density, omega is less than 1, and the universe is open. There isn't enough gravity to stop the expansion, and it will continue forever toward a big freeze. But if the density is exactly equal to the critical density, if omega is precisely 1, then the universe is flat. It is perfectly balanced on a knife's edge. And for decades, our best instruments have told us something remarkable. From measurements of the cosmic microwave background, we have found that our universe is almost perfectly flat. We appear to live on that razor's edge. This fact is its own quiet puzzle. For the universe to be so flat today, it must have been almost impossibly flat near the very beginning. It is an unstable balance, like a pencil standing on its point. Any small deviation should have grown over 13.8 billion years. The fact that we are still here, on the edge, suggests something set this balance with incredible precision. So, what does it mean to live in a flat universe? In a simple version with only matter, the expansion would slow down forever. It would get closer and closer to zero, but never quite reach it. But our universe is not that simple. We have dark energy. And in our standard model of cosmology, dark energy is thought to be a constant, an intrinsic energy of space itself. If that is true, this constant push ensures that even a flat universe will accelerate its expansion, leading us back to the big freeze. This is the central tension in modern cosmology. We live in a universe that appears perfectly balanced, yet it is being pushed off that balance by a force we do not understand. And this is where the story takes a speculative turn. The biggest assumption is that dark energy is truly constant. But what if it isn't? What if this force could change over time? This idea is known as quintessence. Unlike a fixed constant, quintessence is imagined as a dynamic field that can evolve as the universe ages. For years, this was a compelling but theoretical alternative. Then, the data started to come in. Astronomical projects built to map the history of cosmic expansion began to hint at something unexpected. The results, while still debated, showed a slight deviation from what we would expect if dark energy were constant. At a statistical level that is intriguing, but not yet a definitive discovery, the data suggested the strength of dark energy might be changing, perhaps weakening over time. This has opened the door to models once considered fringe. It is important to remember that what follows is one speculative idea among many, built on these tentative findings. It is not established fact, but a glimpse into a possible future. One such model, from physicist Henry Tai and his collaborators, explores what could happen if this weakening is real. It proposes that what we call dark energy is the fading energy of a hypothetical field. In this model, there is also a true, underlying cosmological constant, but it is small and negative. Early on, the field's energy dominated, driving the acceleration we see now. But as the universe expands, this energy fades. If it fades enough, the underlying negative constant could take over. The push would turn into a pull. The expansion would slow, halt, and then reverse, tipping the universe into a big crunch. In this speculative future, our universe has a finite life, ending in fire about 20 billion years from now. The eternal now. This possibility of a future big crunch is a profound shift in thinking. But a reversal is just one outcome of a weakening cosmic push. What if dark energy does not just weaken, but simply fades away? What if its push diminishes over billions of years until it perfectly cancels out the pull of gravity in our finely balanced, flat universe? This is the cosmic stalemate. It is not the infinite slowdown of a matter-only universe. It is not the reversal of a big crunch. It is a hypothetical, breathtakingly precise moment where the expansion rate of the universe hits zero and stays there. The long, quiet war ends in a perfect truce. Imagine what this universe would be like. The outward rush of galaxies would cease. The cosmic web of superclusters and voids would be locked into place, its distances fixed for eternity. The universe as a whole would simply stop growing. Time would not stop. The laws of physics would not change. Locally, planets would still orbit their stars. Stars would still burn through their fuel. The arrow of time would continue to move forward within these systems. But the universe's grand story of expansion would be over. It would enter a state of the eternal now. This is very different from the Big Freeze. In the Big Freeze, accelerating expansion isolates every galaxy. In a stalemate universe, the cosmic web remains. The galaxies would hang in the darkness like sculptures, forever visible but forever unreachable, a single, vast, and static structure. This state is the ultimate expression of stillness. It is not a freezing of temperature, but a freezing of dynamics. And within this static universe, the slow work of thermodynamics would continue. Over trillions of years, the stars would burn out. The universe would grow dark and quiet, just as in the Big Freeze. But the galactic skeletons would remain. The ghostly outlines of our galaxy and its neighbors would hang in the void in their fixed positions, an eternal monument to everything that ever was. No more expansion, no more contraction, just silence. But could such a state ever truly exist? It is almost certainly not stable. The scenario requires an unbelievable degree of fine-tuning. The push of dark energy would have to fade to exactly zero, in a universe where the density is exactly critical. It is a system perched on the tip of a needle. Any tiny fluctuation would tip the scales. A little too much energy, and the universe would begin to slowly expand again. A little too little, and gravity would eventually win, leading to a slow-motion collapse. A perfect, eternal stalemate is likely a mathematical ideal, a universe that would have to hold its breath for eternity. This fragility is why many theorists look to other ideas, like Roger Penrose's model of a cyclical universe, where the end of one cosmos becomes the beginning of the next. The cosmic stalemate is therefore the ultimate outsider theory. A future born from a perfect balance, requiring a form of dark energy that performs a disappearing act so precise it feels almost impossible. It is the most ordered, and perhaps the most unsettling, of all possible ends. The meaning of motion. We began with a choice between fire and ice. But as we have seen, the true story of the cosmos is more subtle. Our journey has taken us to the razor's edge of a flat universe, a cosmos balanced between fates. We've learned that this balance is being disturbed by the enigma of dark energy. And we have discovered that this strange force may not be constant at all. This quiet revelation, whispered by our telescopes, has reopened the book on our cosmic future. It has revived the idea of a big crunch. And it has allowed us to contemplate an even stranger possibility, the cosmic stalemate. A future where the engine of the universe simply cuts out, leaving reality locked in a state of eternal stillness. The ultimate answer to which of these fates is ours lies hidden in the true nature of dark energy. It remains one of the most profound unsolved problems in science. The next generation of observatories, like the Euclid Space Telescope and the Vera C. Rubin Observatory, are designed to hunt for the answer, to finally tell us if we are living through a chapter of a long story, or just before the end of it. The story of the universe has always been one of motion and change. The idea of a stalemate forces us to confront a reality without that motion. A silent, still, and eternal monument. It suggests that all of cosmic history could be just a fleeting, dynamic phase before the universe settles into its final, permanent form. Our existence, our thoughts on a small planet orbiting an average star, are all a momentary flicker in this vast cosmos. Whether our universe is destined to end in fire, in ice, or in an impossible, quiet stillness, we are privileged to be here now, in the brief, warm morning of the cosmos, able to look up at the sky and wonder where it is all going. The debate over the universe's ultimate fate is one of the most active frontiers in science. Let us know in the comments. What do you think is the ultimate fate of our universe? The Big Freeze, the Big Crunch, or the impossible cosmic stalemate? Scientists just realized the universe is heading for a big crunch. You've probably heard the story of how the universe ends. It's a story of ultimate, profound loneliness. A story that ends in a cold, dark, and endless nothing, where galaxies drift apart until the last star fizzles out, leaving behind a silent, eternal void. For decades, this Big Freeze, or heat death, narrative has been the accepted ending to our cosmic story, a bleak, but seemingly inevitable conclusion. But what if that whole story is wrong? What if the grand narrative of our cosmos, the one we've been telling for a generation, is built on a foundation that's now starting to crack? What if the universe isn't doomed to fade away, but to come crashing back in on itself in a final, unimaginable inferno? Because that is the startling new possibility emerging from the frontiers of cosmology. Scientists have found shocking new clues, hidden in the light of dying stars and the map of ancient galaxies, that suggest our universe isn't expanding forever. It's heading for a big crunch. The accepted story, a universe fading to black. To understand just how revolutionary this new idea is, we first need to appreciate the story it's about to replace. The tale of the forever expanding universe isn't just a guess, it's a detailed and deeply unnerving prediction from our best model of the cosmos, known as lambda CDM. The story starts 13.8 billion years ago with the Big Bang. In that fiery instant, the universe began expanding. For the first several billion years, gravity, the pull of all the matter in the cosmos, was acting like a brake, tugging on the fabric of spacetime and trying to slow things down. For a long time, the big question was, what wins? Would gravity halt the expansion and pull everything back together? Or would the universe expand forever? Then, in 1998, came a discovery that changed everything, and earned a Nobel Prize. Astronomers were using distant Type Ia supernovae, the spectacular explosions of white dwarf stars, as standard candles. Because these explosions always have a similar intrinsic brightness, how faint they appear tells us how far away they are. When two teams of astronomers looked at these cosmic lighthouses, they found something completely unexpected. The faraway supernovae were dimmer than they should have been. They were farther away than our models predicted. The only explanation was that the expansion of the universe wasn't slowing down. It was accelerating. This introduced a mysterious new character to our cosmic drama, dark energy. This isn't dark matter, the invisible stuff providing extra gravity to hold galaxies together. Dark energy is something else entirely. It's a strange, repulsive force, a kind of anti-gravity, woven into space itself. According to our best measurements, this energy makes up about 68% of the universe. And it doesn't dilute as space expands. Instead, as more space is created, more dark energy comes with it, creating an unstoppable feedback loop. About 6 billion years ago, the universe hit a tipping point. The density of matter had dropped so much that the persistent push of dark energy finally overpowered gravity's pull. The cosmic tug-of-war was over. Dark energy had won. The expansion began to speed up, and the lambda CDM model, where lambda represents dark energy as a cosmological constant, became the standard story. And this model paints a very specific, and very bleak, picture of the end, a big freeze, or heat death. In this future, the acceleration never stops. Galaxies are pushed away from each other at ever-increasing speeds. First, distant galaxy clusters would vanish from our sky. Then, individual galaxies would cross a cosmic event horizon, their light stretched into oblivion until they disappear forever. The night sky, once full of countless other worlds, would slowly empty out. Our own local group of galaxies would remain gravitationally bound for a while, a lonely island in an endless ocean of emptiness. But the universe outside this island would be gone, forever beyond our reach. Over trillions of years, the stars within our galactic island will burn out. The last red dwarfs will flicker and die, becoming cold, black cinders. The universe will enter a degenerate era, a time of cosmic fossils, black holes, neutron stars, and dead stars. But even that's not the end. Over googles of years, numbers so large they're almost meaningless, even these remnants will decay. Quantum mechanics predicts that protons themselves will eventually dissolve. Finally, through Hawking radiation, even the black holes will slowly evaporate. The supermassive black hole at our galaxy's center will be one of the last to go, vanishing in a final, weak flash of light. What's left? A cold, dark, and featureless void, almost perfectly empty, just fractions of a degree above absolute zero. No structure, no life, no memory, the end of time itself. For a quarter of a century, this has been our scientifically backed prophecy. But now, new evidence is tearing that story apart. The pivot, cracks in the cosmic consensus. The story of the Big Freeze is tidy, elegant, and terrifying. But in science, tidy stories often hide messy truths. For years, small cracks have been appearing in the lambda CDM model, nagging inconsistencies that have only grown more pronounced. The most famous of these is the Hubble tension. Simply put, it's a major disagreement about how fast the universe is expanding right now. There are two main ways we measure this. One method looks at the early universe via the cosmic microwave background, CMB, the afterglow of the Big Bang. When you run that data through the standard model, you get an expansion rate of about 67 kilometers per second per megaparsec. But when you measure the late universe, using nearby stars and supernovae, you get a different answer, around 73. These two numbers should match. The fact that they don't, and their error bars don't overlap, is a 5-alarm fire for cosmologists. It means something, somewhere, is wrong. This brings us to the more direct challenge. The idea that dark energy might not be constant after all. Recent findings are hinting that its strength changes over time. One of the biggest clues comes from the Dark Energy Spectroscopic Instrument, or DESI. Perched on a mountain in Arizona, DESI's 5,000 robotic eyes have created the largest 3D map of the cosmos ever. It measures something called baryon acoustic oscillations, BAOs, frozen echoes of sound waves from the early universe that act as a giant, standard ruler. By measuring this ruler across cosmic time, we can track the universe's expansion history. In 2025, the DESI collaboration released its analysis. When they combined their data with other cosmic observations, a startling hint emerged. The data preferred a model where dark energy is not constant. It appears to be weakening over time. The evidence isn't quite at the 5 sigma gold standard for a discovery, but at up to 4.2 sigma, it's far too strong to ignore. This wasn't an isolated finding. Around the same time, a team from Yonsei University took a closer look at the type Ia supernovae themselves. They discovered a bias. Supernovae in young galaxies are systematically dimmer than those in older ones. This is a potential bombshell. The most distant supernovae we see are in the early, much younger universe. If they're naturally dimmer than we thought, they aren't as far away, and the evidence for acceleration weakens. When the team corrected for this age bias, they concluded that the standard lambda-CDM model was in trouble, suggesting the universe might even be in a phase of decelerated expansion already. But the real game-changer is a new model from Cornell University physicists, published in February 2026. It pulls together all this evidence from DAISY and other surveys and proposes a new mechanism. That dark energy is driven by a field of incredibly light particles called axions, combined with a *negative cosmological constant. In this model, the universe is still accelerating today, but that's just a temporary effect of the axion field. As this field's energy fades, the underlying negative constant will take over, and gravity will win the cosmic tug-of-war. If this model is right, the entire future is thrown into question. The end of the universe is no longer a slow fade to black. It's something far more violent, far more spectacular, and far more final. It would be a big crunch. The Big Crunch explained, a cinematic journey to the end. If dark energy is truly fading to reveal an attractive force, then the future won't be a gentle fade out, but a dramatic reversal. The cosmic movie that's been playing in fast forward is about to be rewound at terrifying speed. So what would this big crunch actually look like? Let's take a journey into this new, speculative future. Phase 1. The Great Slowdown. For now, the universe is still accelerating. But according to the new Cornell model, that's set to change. The first signs would be subtle, detectable only by our most precise instruments. The cosmic expansion would stop accelerating. Then, it would begin to slow down. According to these new calculations, the universe will hit its maximum size in about 11 billion years. At that moment, for a brief cosmic instant, everything will hang in a delicate balance. Phase 2. The Cosmic Homecoming. That pause will be brief. With dark energy's push gone and a negative constant pulling inward, nothing is left to counteract gravity. The great reversal begins. Every galaxy not already bound to us will stop receding and start approaching. The cosmic homecoming has begun. This is predicted to happen roughly 25 billion years after the Big Bang, or about 11 billion years from now. At first, the collapse will be slow. Galaxies that had vanished over our cosmic horizon will reappear, their light, once stretched to infinity, now compressed and racing back toward us. The night sky would become a celestial traffic jam of epic proportions. As the universe shrinks, the background temperature rises. The cosmic microwave background, that cold echo of the Big Bang, will heat up. Its photons, stretched for eons, will be compressed back into infrared, then visible light. The entire sky will begin to glow with a faint, uniform light, the color of a dull red ember. The concept of night would become meaningless. The whole sky, in every direction, would eventually be as bright as the surface of the sun. Phase 3. The Fiery Inferno. Now the collapse gets violent. The total crunch is expected about 20 billion years from now, after a collapse phase lasting roughly 8 or 9 billion years. As the universe shrinks, galaxies begin to collide and merge. Their beautiful spiral structures are torn apart, their stars flung into chaos. Soon, the stars themselves, once separated by light years, will start to collide. The temperature of the universe is now millions of degrees, and the surfaces of stars begin to boil away. Planets are incinerated. The background radiation is no longer just light, it's a deadly bath of X-rays and gamma rays. The very atoms that make up matter are torn apart, resolving everything back into a superheated plasma, just like in the first moments after the Big Bang. There are no more galaxies, no more stars, no more planets. There is only a seething cauldron of fundamental particles and high-energy photons, growing hotter and denser with every passing microsecond. Phase 4. The Final Singularity. In the final moments, the collapse is unimaginably fast. The fundamental forces of nature begin to merge. In the last fraction of a second, All the matter and energy of the entire cosmos is compressed into a point of infinite density and infinite temperature. A gravitational singularity. This is the Big Crunch. The absolute end. A perfect mirror image of the Big Bang, where space and time themselves come to a definitive stop. The rebirth? A universe in a cycle. The Big Crunch is a vision of ultimate, fiery finality. But what if that singularity isn't an end at all? What if it's just a reset button? This is the core idea behind one of the most mind-bending concepts in cosmology, the Big Bounce. The hypothesis proposes that the universe is cyclical, undergoing an eternal series of expansions and contractions. Our Big Bang wasn't a beginning from nothing, but the result of the collapse of a previous universe. The idea fell out of favor for a while because of the singularity problem, a point where the laws of physics break down. But our understanding has evolved. To understand a Big Crunch, we need a theory of quantum gravity. We don't have one yet, but leading candidates like loop quantum gravity and M-theory offer some tantalizing clues. In some of these models, the singularity is avoided. In loop quantum gravity, for example, there's a maximum possible density. As the universe is crushed down, it encounters a powerful repulsive force from the quantum structure of spacetime itself. This force halts the collapse and forces the universe to bounce back outward, triggering a new Big Bang. The Big Crunch becomes a big bounce. Other models, from M-theory, imagine our universe as a 3D brain floating in a higher dimension. Here, a Big Bang is caused by our brain colliding with another, releasing a tremendous amount of energy and starting a new cycle. If the universe is truly cyclical, it could be infinitely old, with no true beginning or end. The matter and energy that make you and me could be the recycled remnants of a cosmos that existed before ours. It even raises the question of whether the laws of physics are the same in each cycle. Maybe our universe is just one successful version in an endless cosmic experiment. The Big Bounce replaces a final death with the promise of cosmic rebirth. We are at a fascinating, humbling moment. For 25 years, we thought we had the final chapter figured out. A universe fading into a cold, lonely oblivion. Now, that certainty is shattered. The story is being rewritten in real time. New data and new ideas have resurrected one of the most dramatic possibilities in all of science, the Big Crunch. And with it, the even more profound idea of a Big Bounce, a cyclical cosmos of endless death and rebirth. So, which is it? A freeze, a crunch, or a bounce? The answer hangs on the true nature of dark energy, the mysterious force that has been secretly writing the universe's final act all along. Whatever the end may be, it's fantastically far away. But the quest to understand it reminds us that we live in a special, fleeting moment. A time when the universe is still vibrant and full of light, and when we, a curious species on a small blue planet, can piece together the clues and dare to ask how it all ends. The cosmos is not done surprising us. It's still writing its own grand finale, one supernova and one galaxy at a time. And we are lucky enough to be here to read the drafts. If this journey to the end of time blew your mind, be sure to subscribe and hit the notification bell for more voyages into the deepest mysteries of the cosmos. And I have to ask, which fate for the universe do you find most fascinating? A cold, infinite void, a fiery final collapse, or an endless cycle of death and rebirth? Let me know in the comments below. Dark energy is tearing the universe apart. Imagine looking out into the total silence of space. Not at an explosion, but at its aftermath. The one that created everything. You would expect it to be quiet now, wouldn't you? The pieces losing their momentum, the initial energy fading. But what if 13.8 billion years after the Big Bang, the pieces of our universe, the galaxies, the stars, the fabric of space itself, were not slowing down? What if they were moving apart faster and faster with every passing moment? Something is pushing everything away from everything else. An invisible, quiet, and overwhelming presence that makes up about 68% of our entire cosmos. A force that is gently pulling the universe apart at its seams. It's called dark energy, and it is perhaps the deepest mystery in all of science. Understanding it is the key to knowing our own ultimate fate. It is the key to answering the final question. How does the story of the universe end? Section 1. A universe that shouldn't exist. For most of human history, our view of the cosmos was one of serene permanence. The stars were fixed points of light in an eternal, unchanging heavens. Then, in the 20th century, that quiet picture was broken. We discovered we live in the aftermath of a cosmic beginning, the Big Bang. And for decades, the story we told about that beginning was a simple one, governed by one of the most familiar forces in our lives, gravity. Think about it. If you throw a ball into the air, gravity pulls it back down. If you could throw it hard enough to escape the Earth, its speed would still be constantly slowed by Earth's pull. The universe, we thought, must work the same way. The Big Bang sent all of matter and energy outward, but the collective gravity of all that material, every star, every galaxy, should be acting as a cosmic brake. For the longest time, the debate in cosmology wasn't if the expansion was slowing down, but by how much. Scientists imagined two possible futures. If the universe held enough matter, and therefore enough gravity, the expansion would eventually stop and reverse. Everything would fall back together in a big crunch, a fiery end that would mirror the Big Bang. If, on the other hand, the universe was not quite dense enough, gravity would never be strong enough to fully stop the expansion. The universe would expand forever, but slower and slower, eventually coasting into a cold, dark, and lonely eternity. A collapse or a coast. A fiery end or a frozen one. These seemed to be the only options. Both were guided by gravity's relentless pull. The situation, as we saw it, seemed understood. The universe was expanding, and gravity was slowing it down. Any other possibility felt unthinkable. It would be like throwing a ball into the air and watching it accelerate into the sky on its own. It would violate everything we thought we knew. And then, we looked closer, and saw the impossible happening. The universe was that ball, and it was rocketing away, faster and faster. Gravity wasn't winning. Something else was. Section 2. Einstein's blunder, or his triumph. To understand how truly surprising this discovery was, we have to go back to the beginning of modern cosmology, and to one person, Albert Einstein. In 1915, he published his theory of general relativity, a new description of gravity. Instead of a force pulling objects together, Einstein described gravity as the result of mass and energy warping spacetime itself. Planets orbit the Sun not because they are pulled by a string, but because they are following the straightest possible path through the curved space created by the Sun's mass. But when Einstein applied these equations to the whole universe, he found a problem. The math told him that a universe filled with matter should be dynamic. The gravity of everything should pull it all together, causing it to collapse under its own weight. This did not fit the scientific consensus of the time, which held that the universe was static, eternal and unchanging. So, Einstein did something he would later come to regret. He adjusted his equations. He introduced a new term, a mathematical fix he called the cosmological constant. This constant acted as a kind of anti-gravity, a repulsive force built into the vacuum of space itself. It would perfectly balance the inward pull of gravity, allowing for the stable, static universe everyone expected. It was an addition he was never comfortable with. Then, in 1929, the astronomer Edwin Hubble observed that distant galaxies were all rushing away from us. The farther a galaxy was, the faster it was moving. The universe wasn't static, it was expanding. Einstein's equations had been trying to tell him this all along. The fix was no longer needed. He discarded it, famously calling the cosmological constant his biggest blunder. For 70 years, that's what it remained. A footnote in the history of science. No one could have predicted that this discarded piece of math would return to become the center of the most profound puzzle in the cosmos. In a way he could never have imagined, Einstein may have been right all along. Section 3. The discovery that changed cosmology. The story of dark energy begins quietly, in the 1990s, with two rival teams of astronomers. One was the Supernova Cosmology Project, the other the High-Z Supernova Search Team. They were on a quest to do what seemed like a straightforward task: to measure exactly how much the universe's expansion was slowing down. Their method involved one of the most spectacular events in the universe, a Type Ia supernova. These explosions happen in a very specific way. A white dwarf star, the dense corpse of a dead sun, slowly pulls material from a companion star. It continues this process until it reaches a precise tipping point, about 1.4 times the mass of our Sun. At that exact mass, it triggers a thermonuclear explosion that obliterates the star. Because they all explode at the same mass, they all have nearly the same brightness. This makes them standard candles. Imagine a row of identical light bulbs stretching into the distance. By measuring how dim they appear, you can calculate how far away they are. Type Ia supernovae are the universe's light bulbs. The plan was simple: find these distant explosions, measure their dimness to determine their distance, and measure their redshift to determine their speed. By comparing distance and speed, they could map the expansion of the universe over billions of years and see how much gravity had slowed it down. They expected to find that the most distant supernovae were moving away faster than the universe is today, from a time before gravity had as much time to apply the brakes. The team spent years scanning the skies. As the data came in, something was not right. The most distant supernovae were not brighter than expected, they were dimmer. Consistently, inexplicably dimmer. This result made no sense. For a supernova to be dimmer, it had to be farther away than its speed suggested it should be. The only way for it to have traveled so much farther was if the expansion of the universe hadn't been slowing down. To cover that extra distance, the expansion must have been speeding up. Both teams checked their data for any possible error. Could dust be making the supernovae look dimmer? Could ancient supernovae have been different somehow? Every alternative was investigated and ruled out. The conclusion, however strange it seemed, was unavoidable. In 1998, they published their results. For the first 7 or 8 billion years, the universe's expansion was slowing down, just as predicted. But then, something changed. A mysterious repulsive force began to overpower gravity. For the last 5 to 6 billion years, the universe has been expanding at an ever-increasing rate. The discovery was so important it earned the team's leaders the 2011 Nobel Prize in Physics. And it gave a name to the cause of this acceleration: dark energy. Cosmology would never be the same. Section 4. The Ghost in the Machine. The discovery of the accelerating universe was like finding a quiet, unseen presence in the cosmos. Scientists suddenly had to account for a new, dominant component of the universe, one whose existence no one had suspected. The name, dark energy, is simply a placeholder, a label for our own deep ignorance. Here's what the discovery meant. The energy budget of our universe is dominated by this strange new component. About 68% of everything is dark energy. Around 27% is dark matter, another mysterious substance whose gravity holds galaxies together. And a mere 5% is the stuff we know: every star, planet, and person. All of visible reality is just a tiny fraction of what exists. It is important to distinguish between dark energy and dark matter. While they share the name, dark, because they do not interact with light, they are thought to be unrelated, with opposite effects. Dark matter is gravitational. It pulls things together. Dark energy is anti-gravitational. It pushes things apart. The history of the universe is a slow, cosmic tug-of-war between these two. For the first 9 billion years or so, matter had the upper hand, and its gravity slowed the expansion. But as the universe expanded, the matter grew more diluted. Dark energy, however, seems to have a strange property. Its density appears to be constant. Imagine an expanding box. As it grows, the matter inside it thins out. But dark energy is different. It does not seem to dilute. It appears to be a property of space itself. As more space is created, more dark energy comes into being with it. This creates a feedback loop. More expansion means more space. More space means more dark energy. And more dark energy means even faster expansion. About 5 billion years ago, the universe expanded to a point where the density of matter dropped below the constant density of dark energy. At that moment, the tug-of-war tipped. The repulsive push of dark energy overwhelmed the gravitational pull of matter. The era of acceleration began. We are living inside that process right now. Section 5. The prime suspects. So, what is this dark energy? The honest answer is, we don't know. But physicists have two main ideas, each with its own profound implications. The first, and leading, suspect is Einstein's biggest blunder, the cosmological constant. In this view, dark energy is simply the intrinsic energy of empty space. According to quantum physics, a vacuum is not empty at all. It is a sea of virtual particles that flicker into and out of existence. This quantum activity should, according to general relativity, have a gravitational effect. It should fill the universe with a constant energy density. A cosmological constant. It's a simple and elegant explanation. But there is a problem. When physicists try to calculate how much of this vacuum energy there should be, their answer is wrong by a staggering amount. Their prediction is about 10 to the power of 120 times larger than what we actually observe. This is the single worst theoretical prediction in the history of physics. It tells us that something is fundamentally broken in our understanding of how gravity and quantum mechanics connect. This disagreement has led some physicists to consider a second possibility, quintessence. The name comes from the ancient concept of a fifth element. It proposes that dark energy is not a constant, but a new, dynamic energy field that fills all of space. Unlike the static cosmological constant, a quintessence field could change over time. Its strength could evolve. Recent observations from projects like the Dark Energy Survey are making this idea more compelling, suggesting dark energy might not be constant after all. This opens up a new range of possibilities, and has dramatic implications for the ultimate fate of the universe. Section 6. The Hubble tension. As if the mystery of dark energy weren't enough, it is connected to another deep puzzle. It's a quiet crack in the foundation of our cosmological model, a problem that has been called a crisis in cosmology, the Hubble tension. The Hubble constant is the number that describes how fast the universe is expanding today. The problem is, we have two very precise ways of measuring it, and they do not agree. The first method is the local measurement. This involves looking at stars and supernovae in the universe around us today. These measurements consistently give a value around 73 km per second per megaparsec. This means for every 3.26 million light-years of distance, space expands 73 kilometers faster every second. The second method is the early universe measurement. This involves looking at the faint afterglow of the Big Bang, the cosmic microwave background. By studying this ancient light and using our standard model of cosmology, scientists can predict what the expansion rate should be today. This method gives a consistently lower value, around 67 km per second per megaparsec. This is not a small disagreement. The gap has only become more persistent as measurements improve. It's like having two perfectly built clocks that are ticking at different rates. Either one of our measurement techniques has a subtle flaw that no one can find, or our standard model of the universe is incomplete. The Hubble tension may be a clue, a quiet signal that dark energy is more complex than we thought, or that our cosmic story is missing a key piece. The ultimate fate. How does it all end? All of this leads to one final question. What happens next? What is the ultimate fate of our universe? Based on what we are learning about dark energy, there are a few possibilities. Scenario 1. The Big Freeze. This has long been the most widely accepted scenario. It assumes that dark energy is a cosmological constant, a steady, unchanging force. If this is true, the acceleration will continue forever. In about 100 billion years, all galaxies outside our local group will have been pushed beyond our cosmic horizon. Their light will no longer be able to reach us. The night sky will become empty. Over trillions of years, star formation will stop. Existing stars will burn out. Eventually, black holes themselves will evaporate. The universe will approach a final state of heat death. An infinitely vast, cold, dark, and perfectly uniform void. It will not end in fire, but in an eternal, silent cold. Scenario 2. The Big Rip. This is a more violent possibility. It depends on the idea that dark energy is not constant, but a form of phantom energy that grows stronger over time. If this is happening, the cosmic acceleration will become hyperacceleration. This ever-strengthening force would eventually overcome not just the gravity between galaxies, but all the forces that hold matter together. In the final moments, stars, planets, and even the atoms themselves would be torn apart. Finally, the fabric of spacetime itself would be ripped. Scenario 3. The Big Crunch. There is a third path. For a long time, this was seen as unlikely. But that picture is beginning to change. What if dark energy is a form of quintessence that is not only changing, but weakening? Recent data from large-scale surveys of the cosmos has suggested this might be the case. If the repulsive force of dark energy fades, the cosmic tug-of-war would tip back in favor of gravity. The expansion would slow, halt, and then reverse. The universe would begin to contract, slowly at first, and then faster. Galaxies would rush toward each other. The universe would grow hotter and denser, until everything collapsed into a final singularity, a Big Crunch. Some theories even speculate this might not be the end, but part of a cycle. A Big Bounce could trigger a new Big Bang, in an eternal cycle of cosmic death and rebirth. Living in the mystery, we live in a quiet, extraordinary moment. Less than a century ago, we believed we lived in a static universe. Less than 30 years ago, we were convinced it was expanding but slowing down. Today, we find ourselves in a runaway universe, propelled by a silent energy that makes up the vast majority of existence. The puzzles of dark energy and the Hubble tension are a profound and humbling reminder that our best theories are incomplete. We are explorers who have just arrived at the shore of a vast, unknown ocean. The search for the nature of dark energy is more than a scientific quest. It's a search for our own cosmic story. To read the first page, understand the middle, and maybe glimpse the final chapter. We are the part of the universe that has evolved the capacity to look back and wonder, to piece together the clues, and to ask these questions. We live inside a great unfolding, balanced between the pull of matter and the push of the void. And the search for what lies in that darkness is, ultimately, the search for the story of everything.